the very first one to focus on the study of black holes before they became so popular these days that you can see them on the front pages of major newspapers. It looks like black holes are now a reality and people are thinking about going there and visiting those places. But just a few years ago, it was an esoteric field. And in fact, if you go back 80 years ago, even Einstein thought that they may not exist. And so 100 years after the formulation of the general theory of relativity, LIGO confirmed their existence. But that was still conceptual. And as of a few weeks ago, we were lucky to see an image. And we're very proud of the Event Horizon Telescope team that are partners of the Black Hole Initiative in making this image a reality. So now, people can relate to images much better than concepts. If you tell them that the LHC discovered the Higgs boson, that's not as compelling as showing them a picture of a black hole. And so now, black hole astrophysics is a major frontier, and in a way, the Black Hole Initiative sort of anticipated that a couple of years earlier. And we are very glad to be working on black holes. Astronomers, philosophers, mathematicians, and physicists, all working on this subject that is very exciting and attractive. And there is a chance of testing those ideas that we come up with future data. So that's a new reality that we live in, and we are all very fortunate to be living at such a time, special time. And so I wanted to welcome all of you on behalf of the Black Hole Initiative. My name is Avi Loeb. I'm the director of the Black Hole Initiative, and we all look forward to many exciting talks in the coming 2.5 days. And just a brief note that questions will be allowed at the end of each talk. So please do not interrupt the speakers, because we have a very tight schedule with lots of talks, limited amount of time. Other than that, I hope you all join us also for the banquet on Tuesday evening. And I'll let Mislav start the first session.
Thank you, Avi. Good morning, everyone. My name is Mislav Bolokovic. I'm a postdoctoral fellow in astronomy at the Black Hole Initiative. I will be chairing this first session. We have an hour and a half and 3 speakers. So as Avi said, we would like to reserve the last 5 minutes for each speaker for questions. And there will be a microphone going around. Everything's recorded, so it will be better if people speak into the microphone so that it's recorded well. So we have 3 talks. The first one is in astronomy, then we have a philosophy, and then a physics talk. Our first speaker is Professor Chungpei Ma from the University of California, Berkeley.
Hey, it's a great pleasure to be here to speak about, like Avi said, the exciting new era after the EHT imaging of the first black hole, first image. And I used to use this slide, but now thanks to the EHT, I can use this one. And you know that you've made it if you have a cartoon dedicated to you in the New Yorker. Okay, thank you very much. Okay. So I would like to focus on the masses of supermassive black holes, i.e., how do we find them locally? I'm talking about the hundreds of them that have direct dynamical mass measurements. So by local, I'm referring to things out to about 100, 150 megaparsecs. Okay, obviously, there are a lot more indirect mass measurements from quasars, AGNs, active galactic nuclei, and others, but there are only about 100 that are modeled very carefully locally that have a direct mass determination. And we're going to hear more talks, I think, from Amy and Priya later about the early seeds of these massive black holes. So for these 100 black holes-ish, there are 4 tracers that people use to infer its mass. Obviously, we need to use something luminous to measure the dark mass. And the probably most frequently used tracer are stars. But we need to resolve the stellar motions very close to the hole within the so-called sphere of influence of the gravity. Otherwise, if you're too far away, obviously the mass would be dominated by stars or dark matter. Okay. And ionized gas is the second tracer. Masers, and more recently, molecular gas, especially with the advent of the ALMA array. There are a few new measurements coming from disk very close to the black hole emitting CO. So very brief sort of summary of these 100-ish black holes are shown here in the so-called M-sigma relation. I'm not going to go into the scaling relations today, but I just want to highlight the y-axis, the vertical axis, where we see about 4.5 dex in black hole masses from 1 million up to 20 billion solar masses, and more below 1 million solar masses, more black holes are being discovered right now. And I just want to highlight the wide range, and every single data point here took a lot of work by various teams over probably 25 years of effort to arrive at this plot. And I want to highlight a few. So this was compilation from our 2013 paper. And there have been a number of new discoveries, starting from the very high end, which my team is targeting. NGC 1600 I'll talk about in a bit. And then these three red stars are compact galaxies that have been recently been discovered, again using stellar dynamics. And here I'm adding 5 diamonds, and these are new determinations from CO, the kinematics of CO gas. You can see they're in a somewhat smaller galaxies, and yet on the smaller range, the triangles are from new masers measurements, and more are coming in. Okay. So I would like to focus today on the stellar kinematic measurements of local supermassive black holes marked by stars here. The triangles are masers, circles are from ionized gas, and the diamonds are from CO. Okay. And just to highlight a few properties, facts about these stellar mass measurements of black holes. Sagittarius A star, we'll hear more about that, I'm sure, in this conference. The supermassive black hole at the center of our own galaxy is the only one for which individual stellar orbits can be mapped. Beautiful results have been coming out from the gravity team and the UCLA Galactic Center team. But I would like to talk about the rest of them. And for all other black holes, there are too far for individual stellar orbits to be resolved. So we use integrated light. So it's like a swarm of bees. The one at the Galactic Center, we can study individual bee motions. But when you go to even M31, no longer can we see individual bees. But by measuring integrated motion from a swarm of bees, which we can't really resolve individually, we still get a lot of information. We get the velocity distributions for what a group of stars are doing, and from which we can still infer the dynamical mass of a black hole. But I want to emphasize that few systems on that M-sigma relation have independent masses from multiple tracers. Most of them just had one measurement from one of the 4 tracers. And the reason is it's very difficult to find a suitable system where you can do measurements from both tracers. For example, CO gas tended to come with dust. When you have dust, it's very difficult to measure the underlying stellar light to get its velocity dispersions and velocity distributions. However, there are a few systems for which we have multiple tracers, therefore we can get independent masses, and that's a very important, obviously, check on the systematics of each measurement. For example, the first beautiful maser system, NGC 4250A, some people here are actively involved in that, was first discovered by masers, but also it has subsequent systematic stellar mass kinematic measurements, which agree beautifully with the maser's measurement. But M87 famously has had 2 different measurements based on stellar light and ionized gas light emission. And they differ by about a factor of 2. And now with the exciting EHD measurement of the black hole, we all know that it agrees beautifully with the stellar dynamical mass of about, depending on the distances you use and so on, it's about, for the stellar mass is 6.2 or 3 billion solar masses, and the event horizon measurement is 6.5, I believe, billion solar masses. Okay, but the error bars are consistent. But the gas measurement is a factor of 2 lower. And I know the gas measurement team is now reanalyzing their analysis. It's possible that the assumption of a Keplerian motion for the disk is too simplistic, and they're studying possibly including infalls. And why is this important? Why is it important to really improve on our local dynamical measurements? And I would like to draw an analogy to the distance ladder in cosmology, where we know that each rung of the ladder has to be calibrated to the lower rung. Okay. And you start out with the local ones. You hope you're getting the radar ranging and parallax distances right, and then you move up. But by moving up, obviously, it increases the volume, and you get many, many more measurements for demographic studies. In this case, you can measure the expansion rate and acceleration of the universe. For the black hole on the right-hand side, I would say similarly. For a long time, the local 100-ish measurements, I'll call it the lowest rung of the black hole mass determination. And there are many others based on reverberation mapping, for example, technique. These study typically, you need to have time variabilities, so these will be AGNs, more distant active galaxies, further out to even quasars at redshift 4, 5, 6. Black hole masses have been indirectly inferred from line widths and so on, but they always have a coefficient that has to be calibrated to the local measurement. You need to find a system that has both measurements. Okay. But thankfully, now we have at least one more data point through direct imaging. So that's a critical point for us to compare to. So how do we do this? Well, we need really the most powerful telescopes and computers, supercomputers, to do the stellar orbit modeling. Okay. So I want to just use M87 as an example to just highlight a few things that we are now doing to revisit the Gebhardt et al. 2011 black hole dynamical mass measured from stellar kinematics. Okay. And this is the team with 3 graduate students at Berkeley, and Janelle Walsh and John Blakesley collaborating on this project. And I don't have a number to report today, but I want to describe to you, we're working very hard on this. But I want to describe to you some new inputs we're using, new analysis. So number one to remember is, obviously, we need spectroscopic data, very high signal-to-noise stellar spectra. These are absorption line spectra that could resolve the sphere of influence of the black hole. Okay. So Gebhardt et al. Actually obtained beautiful data. At first, we were wondering whether we should get new data. But then we dug out the Gemini NIVS adaptive optics, 23 exposures, each one of 10 minutes, is archival. So we actually reduced the raw data. And just to remind you, these are beautifully resolved, spatially resolved spectra using an integral field spectrograph. So in one exposure, we have spatial coverages in X and Y in 2D, and we can get many, many spectra. Okay. So again, this is preliminary work, but I will want to just compare for you. On the left is a figure 3, I think from Gebhardt et al. 2011, for which the 6.2 or 3 billion solar mass black hole was determined. They spatially bin the spectra to reach a given signal to noise. We typically need 80 or 100 per spectrum, so it will be 80 per pixel for each bin in order to measure the stellar velocity distributions accurately enough. Okay. So we analyze the same data, and you're seeing this 3 by 3 arc seconds field of view of the NIFS instrument on Gemini. And on the right is it's the same data, but our new reduction. And for a similar signal-to-noise requirement, you can see we're obtaining at least 200 spatial bins. It depends a bit on your threshold. If we lower a little bit, we can get to 300 plus spatial bins. For each bin, we have a stellar absorption line spectrum for which we can measure the velocity distributions. And I don't know, I know how we got ours. I don't know why Gebhardt et al. Was only able to get 40 bins, but that was really a pioneering work and an incredibly important analysis, and they really got beautiful data. Okay, so we are proceeding with the right with our new bin, beautifully spatially resolved information. Okay, so just to highlight a couple spectra we're obtaining right now from the NIFS data for M87, you're seeing the top is a bin that's, a 0.28 and minus 0.35 arc seconds away from the central AGN, and you're seeing the CO band heads. And the bottom is another, for example, one of the many spatially binned spectra we have. So the way we usually try to obtain this velocity distribution is by fitting a template, stellar template, and then we broaden it with a full velocity distribution line of sight, f of v, and red is the best fit broadened stellar distribution. And so from that, we can determine the f of v. So we don't just determine the radial velocity, or the sigma, the dispersion, but we also get the skewness, kurtosis, and the higher moments. And we don't assume a Gaussian distribution. And the tails are very important for black hole measurements. Okay. So that's number one. We are improving on the spectroscopic measurements. For black hole mass modeling, it's also very important to have very well mapped photometric surface brightness profiles for the stars, because we want our orbit model to be able to reproduce basically exactly the stellar spatial distribution. Okay, that's a very important constraint in addition to the kinematic constraint. So this is a spatial constraint, and we use them simultaneously in the short orbit modeling. So again, Gebhardt, the pioneering work, they used the 1991 HST WIFPIC data of M87, and was published in Lauer 2002, and was two short exposures. And again, that was really the first beautiful HST data of M87. But since then, a lot of improvements have been done. There was a huge HST ACS Virgo cluster survey. Okay, so now, with John Blakesley on the team, we are, again, reanalyzing the archival data. As you can see, Hubble has spent 50 orbits on M87. Okay, and with the usable data are shown here. So this is an extremely deep image of M87. And here is our current reduction, where you can see the beautiful jet, which is being we have to mask it out. We don't want to study the jet here. We want the underlying stellar spectroscopy. And you can see the counter jet below that, the little black part. And all the black dots here are globular clusters for the most part, and we don't want them. So we actually mask them out. Okay, so we're measuring the 2D surface brightness profile, which we will use. We'll deproject it, and we'll use that as a constraint in the short orbit modeling. Okay, so that's a photometry improvement. And the last piece we are improving on is the very important piece that we need to use in order to tease out the black hole mass. And that's the stellar orbit modeling. I won't have time today to go into the details, but it's a well-established method in which we generate hundreds of thousands of allowed stellar orbits for a given gravitational potential, which we assume there's a black hole of a given mass we want to constrain. There's a stellar profile, which we used, but we have a mass-to-light ratio conversion that's a free parameter. And then if your data go out far enough, we also want to include dark matter parameters. Okay. And one important assumption made in Gebhardt's paper, and that was the standard assumption that had been used for a long time, is to assume that the gravitational potential is axisymmetric. And this simplifies the library tremendously, and this has been tested. There are a few codes that you can compare results with. Okay. And also, as I mentioned, there are these parameters in addition to the black hole mass one needs to model. And standard practice is to just do a direct grid search. You have a grid in black hole mass, a grid in mass-to-light ratio, and perhaps other dark matter parameters. But this immediately becomes very expensive if you go beyond 2 dimensions. So the improvement we're making right now is we've spent more than a year now on the triaxial short orbit code based on the code developed by Remco van den Bosch, but we are making significant tests on this and improvements to that. And we would like to relax the axisymmetric assumption. And these slow rotating giant elliptical galaxies like M87, axisymmetry is probably may not be a very good, I mean, it may be okay assumption, but it may not be good enough now that we want more precise measurements. And recent MUSE data have shown that the stellar kinematics twist on some scales, and usually when they don't behave very smoothly, it's a hint of triaxiality. That is, you can't assume B and C to be the same, or A and B, two of the axes to be the same. Okay. And also to speed up the search, because once we allow for triaxiality, there are more parameters. We really can't do the brute force research. So we are implementing a Bayesian optimization method. I think it's about time that the black hole mass modeling community move into a machine learning, sort of the modern age search method. Okay. So I don't have a number to report, but we are working very hard. We're seeing chi-squared minima, but we want to test many things before we want to release the answer. Okay. So just very briefly, beyond M87, okay? So we have been working on this massive survey, which is a volume-limited survey of the 100 most massive galaxies by stellar mass out to a fixed volume, in this case 102 megaparsecs, chosen to include the Coma cluster. Okay. And we not only want to study black holes, we also want to study the formation of massive galaxies. But I just want to highlight the two most massive black holes that have come out of the survey so far. And again, the left is the NGC 1600 black hole at 17 billion solar masses, so about almost 3 times more massive than M87. And on the right is NGC 4889, the Coma cluster's brightest galaxy of comparable mass. And already just with 2 systems of comparable black hole masses, we're finding that they live in very different environment. The Manhattan of the universe on the right, and the sort of small Midwest town on the left. Okay. How they became so big in different environments, I think is a very interesting question for simulators to address. But I want to just go on highlighting these other 20 galaxies for which we just published the 2D IFU kinematics, and led by graduate student Irina Enna. And here I'm only showing the velocity dispersions. Of course, we have the V, the skewness, the kurtosis, and the higher velocity moments. Okay. And you are seeing for each panel is the galaxy. The y-axis is the velocity dispersion of the stars, and the x-axis is the, obviously, distance from the center of each galaxy. But note that this is on logarithmic scales, because our 2 data sets span now a factor of more than 100 in radial range. And the Gemini's GMOS data, the magenta one, allows us to really go in, okay, to probe the sphere of influence of the black holes. And at a given radius, you're seeing multiple data points, and that's because we have IFU data. So we have azimuthal information too. We're just compressing all the information onto the radial plot. Okay, you can also see most of the velocity dispersions are rising towards the center. That by itself hints at the presence of supermassive black holes, but we need to be careful. Velocity anisotropies can mask a supermassive black hole. That's why we need to do a very extensive stellar orbit modeling using the orbit code. Okay. But now the data are all ready, and we are systematically modeling them. The stellar orbit modeling part is very expensive. Okay, so that's the massive survey, and we have data for at least 10 more. Not every galaxy can be resolved, so we can't do this for all 100 galaxies, and that will be super expensive too. But I just want to go a couple slides beyond the massive survey. Okay. As I mentioned, the massive survey does target the most massive 100 galaxies, so we expect to probably find the most massive black holes out in this volume in the northern hemisphere. Probably in our sample. But we would like to ask, what about if we go beyond 100 megaparsecs? So currently, as you saw in the M-sigma relation, only 3 black holes have direct mass measurements larger than the 6 billion solar mass ones in M87, the three measured by us, and these are the masses up there. But what I'm showing here is the HST, surface brightness profiles of the stars, okay, for the three galaxies. And you can see already, so this is the y-axis is just the, basically the amount of stars per area. So you can see it doesn't follow the standard vocal lure or Cercic profile, which would be much cuspier, okay, would be a power law extending to the center. But instead, they all flatten. Okay, so there's a characteristic core radius, additional information imprinted on the surface brightness stellar distribution. And most of us think maybe it's due to binary black hole core scouring, kicking out these stars. Okay. But the observational fact here is there is a deficit of stars at the center of these giant galaxies, and it makes observations incredibly difficult because we need to get high enough signal to noise to get a high signal to, we need to get really high, just really long exposures in order to get high enough signal to noise for the spectra. So there are, however, other galaxies who have even bigger cores. And in our 2016 paper, we showed a new correlation of the black hole mass versus the core radius. And they are very, very tightly correlated. So now, rather than looking for high sigma galaxies or high stellar mass galaxies to find where the most massive black holes are hiding, we can use core radii as a proxy. So we now know there are a number of large core radius black holes beyond 100 megaparsecs. Here I'm showing you two examples. But you can see they're really faint at the center. And GMOS, NIFs, no good for these galaxies. You just can't possibly get a good enough signal to noise. So now the new toy on the horizon is the KEC KCWI, new integral field spectrograph. Okay. So we are now using the KCWI to target these extremely large and faint core galaxies. And here I want to just show you our preliminary data. We were able to get these are two different bins of a galaxy we observed last summer. And you can see the beautiful calcium H and K lines all the way to the magnesium B lines all here. And black are data, and red are our best fit broadened templates. So we can use these shapes of these absorption lines to determine, again, the velocity distributions. And then we will feed this into, we're feeding this into the stellar orbit modeling code to determine the black hole masses. Okay. So just a couple slides about the exciting future. So we're targeting a few galaxies using KCWI. It's pretty expensive. We need multiple nights to do one galaxy. And the weather has been awful. Okay. So some just exciting prospects I want to come back to. There'll be a lot of discussion about the Event Horizon results, obviously. But I think it's natural to ask, are there other candidates? Okay. So one can just start out with a known mass, with a distance to at least determine the angular size of the event horizon. And you can multiply by a factor 5-ish to get the shadow size. And we're eagerly awaiting your results for the Milky Way black hole. But in GC 1600, as I mentioned, it's at 17 billion solar masses, but it's at about 54 megaparsecs. So it's about 3 times further, about 3 times larger than M87. So the event horizon itself size is not so much smaller. Okay? But the problem right now is there is no known millimeters of millimeter emission. Okay? These are extremely quiescent galaxies, stars, because you saw the spectrum, there are no emission lines. It's extremely quiet. Okay. So the question is, are there others? So everything has to work, right? The black hole mass has to be big enough, distance has to be small enough, you can resolve it, then you need to have emissions. And I think hopefully the massive survey, as we find more, we can provide you with more candidates. Okay. And just the last slide to look forward, there will be a lot more talks about binary supermassive black holes and binary stellar mass black holes on the left. Okay, so for the supermassives, we can do pulsar timing or the LISA. And on the right, obviously, we want to do better dynamical measurements. And again, these measurements allowed us to probe the high redshift black holes, and together we can really study. We want to know beyond just local to black holes, we would also like to know how they form, how they assembled. And to answer these questions, we need to find black holes for the entire cosmic history. And these new instruments will allow us to go further. Thank you very much.
Avi has a question.
So one of the novelties of Gebhardt's paper was to include dark matter, which was not included in the previous analysis. And the alarming result, as far as I'm concerned, was that the concentration inferred by Gebhardt was 15, which is unheard of for brightest cluster galaxy. So, in fact, they got, if they used NFW, they got a very tight core for the galaxy. And to me, it sounded like the case of the disk is more compelling because the dark matter concentration was so high. And so can you elaborate about your findings for the dark matter, not the black hole, but do you find that indeed the dark matter concentration is much larger than we expect?
No, we are not finding that right now. We are still searching the parameter space. One thing to note is their mass to light ratio is very high too. It was 9.1 in the V band, which is uncomfortably high compared to other systems. And presumably, if you resolve the sphere of influence well enough, you shouldn't worry about the dark matter. But some of the orbits are on very eccentric, stars are on very eccentric orbits. So it's really sometimes important, even if you don't model, the dark matter in your modeling, to really, you really need to model the potential on the outskirts. So if it's not stars, it has to be dark matter. And also, they searched the parameter space separately for 2 different data sets, so because it's very, very expensive. So I think with the Bayesian optimization, we can search, for example, 5 parameter space simultaneously much more efficiently. So I don't have a direct answer for you, but for the other black holes we're modeling in the massive survey, we found NFW not to be preferred. It doesn't want the dark matter to stick out because the star distribution is so flat. When it sticks out, the model really doesn't work. It really wants a single point at the center and the stellar mass. And we're hoping to be able to constrain actually dark matter profile somewhat. And I think dynamically it makes sense. I think it was hard to sustain a cusp in the dark matter with the flat stellar distribution.
So in the case of M87, where we have the Gebhardt 2011 stellar dynamic measurement being closer to the HT value, and then the gas dynamical measurement was half as much for the mass. Is there any consistency or in the direction of a systematic error in terms of the stellar versus gas dynamical measurements when these are both available?
Yeah, as I mentioned, there are very few systems with both measurements, and it would be nice to identify more. There is one other system where the gas mass was, again, about a factor of 2 lower. I think it's 1132. There are a couple others where the 2 agree quite well. Okay, and the 4258, the Mazur's measurement is just gorgeous. The stellar dynamical measurement agrees. So it's sort of up in the air that I would say half of them agree, the other half don't agree, and I think we really need more measurements, but they're incredibly difficult. Only for 2 systems, M87 and 1132. Yeah.
So just curious, right now that the modeling techniques have become much more sophisticated, as you're showing us very nicely, many of these are actually BCGs in the case of, say, M87, right? And they're sitting with high X-ray emitting hot gas. Do you actually require that additional component when you model the larger scale? Is that, are you at a regime where that's starting to become important or not really?
Yeah, that's a very good question. Like for the massive survey, we have our Chandra archival data for quite a few of them. we are really just modeling within basically one effective radius of the galaxy. So we are not sensitive to sort of the group scale or cluster scale hot gas. And I think within one effective or two effective radii, the X-ray gas is a very small component of the, I mean, it would be great if we were able to measure that independently.
So it's still at the moment, even with the much more sophisticated modeling with higher order velocity moments and stuff, it's really a very small perturbation.
That's right, within in that volume.
So it's very interesting to me that you're introducing more models using the triaxial models. Naively, I would assume that means that the uncertainty is going to go up. Is that what you expect to happen, or do you think because you're more precisely analyzing the data, you're going to get a more accurate, more precise measurement?
I think we want to answer that exact question you are saying. If we were using exactly the same moments, I think that Gebhardt published, then absolutely. Then, I mean, I think that another way to say it, the systematic error should be larger. But now we were somewhat surprised that we're able to get so many more spatially resolved bins. So that may help in also our reduction method. Everything is different. So I think it would be very good. Obviously, we are checking their axisymmetric mass first. We're running our code in that limit, which turned out to be very difficult, but it's a different story.
Okay. We don't have more time for questions, but there will be time for discussion later. So let's take the speaker again. Our second speaker for today is Professor Daniel Kempik from University of Arkansas.
Well, thank you very much for having me. I'm going to have a little change of pace and talk about history. Next week is going to be the centenary of the 1919 eclipse expeditions, which famously confirmed Einstein's theory of relativity and made Einstein overnight into the celebrity that he remains to this day. This story is very well known. It's been told many, many times, and as can happen when a story is told many times, especially when you're not sure that you have your audience's attention for very long, the story has gotten a little streamlined over the years. The number of characters has been reduced a little in many retellings, sometimes just to two, Einstein and Eddington. There has been a certain focus on topic and even on field, so that, you know, if you're giving a popular account of the 1919 eclipse expedition, once you've introduced your audience of lay people to the theory of general relativity and gotten them to the point where they understand what it was all about, then you probably feel like you've done enough work for one day. And you don't talk at all about the astronomy, and after all, this was, in fact, these were astronomical expeditions. So this is the centenary year. I felt like it's a bit like in the medieval banqueting hall. For once you have your audience's attention, maybe you're going to give them the whole epic story with all of the characters and all of the events. So I decided, why not write a book for the centenary? This is the cover of the book. My purpose is to reintroduce people to some of the other characters, and in particular to some of the astronomy that was done. So without further ado, I felt like I have to show this image. I am not going to tell you anything about it, except to draw some parallels with 100 years ago. It's remarkable that this image should have come to light in the centenary year of the 1919 eclipse expeditions, because after all, there are some important parallels. Because in both cases, we're interested in photons moving in a gravitational field and how they respond to the gravitational field. You'll remember that a little over a century ago, certainly in the late 19th century, many people felt that light didn't respond to gravity. And so Einstein had drawn their attention to an important part of physics that had been somewhat neglected at that time. So the team from 1919, especially Eddington, who we'll come to in a minute, said this expedition was about weighing light, about showing the way that light behaves in a gravitational field. And just as today, in resolution terms, this is a remarkable breakthrough. So the task that faced the team of astronomers in 1919 was at the very frontier of what could be done at the time with sub-arcsecond differential astrometry to see if there were slight shifts in position of stars when they were seen close to the sun. Okay, so it was Einstein himself who proposed the test, so you hopefully are familiar with the idea that Einstein realized that his principle of equivalence demanded that light react into a gravitational field just as everything else is and should fall in a gravitational field. And as early as 1913, he wrote this letter, this is Einstein's handwriting, to the great American astronomer George Ellery Hale, pointing out to Hale that light should be deflected. So you can see the lower diagram there shows the light from a star passing close to the sun and being deflected by a small angle as it falls towards the sun. And the idea would be to check if stars seen close to the sun are deflected by this small angle in their apparent position in the sky. But of course, we can't see stars close to the sun in the daytime. And Einstein realized from the beginning that this would require astronomers to travel to observe a total solar eclipse. In this letter, he actually asks Hale, well, do we have to go to an eclipse? Because he was aware that that wouldn't be easy. Down at the bottom, you'll see the words by Tage underlined. So he says, could we do this in the daytime without a solar eclipse? And of course, Hale wrote back and said no, and said, well, here are some people you might want to talk to who might be able to do this experiment going to an eclipse. In fact, as some of you may know, Einstein himself helped raise money for an expedition to the Crimea in 1914 to observe a total solar eclipse. Of course, it was a German expedition. The eclipse took place in August 1914, and if you know your history, you'll know that earlier in the same month, World War I broke out, and so the poor German team of astronomers were arrested by the Russians as enemy aliens and never got anywhere near observing the eclipse. So that gives you some idea of the difficulties of eclipse expeditions. That's a little rare, maybe getting arrested, but of course, weather and other problems make it not a very easy thing to do. And of course, you can also have problems not only with the location and the timing of eclipses on the Earth, but also in the heavens, right? Sometimes an eclipse can take place where the sun is not particularly near any bright stars. So when Einstein's theory, when he had finally succeeded in attracting astronomers' attention to this topic, two British astronomers, Sir Frank Watson-Dyson, who was England's Astronomer Royal at that time, and Arthur Stanley Eddington, apparently it was primarily Dyson who realized that the 1919 eclipse was the perfect eclipse for testing the theory because the eclipse took place on May 29th when the sun is in the star field of the Hyades, which is the closest star cluster to the Earth, and so there would be a particularly rich field of bright stars close to the sun. So that would be the ideal time from a celestial point of view to conduct the experiment. Of course, it was also a particularly bad time from, as we'll see in a minute, from the point of view of the Earth, because World War I, as they were doing the planning, World War I was still raging. Now, what I particularly want to draw your attention to, here's a picture of Einstein and Eddington together. This picture was taken at the Cambridge Observatory, of which Eddington was the director. In recent decades, there has been a sort of a counter story to the eclipse expeditions, which charges that Eddington in particular was biased in favor of general relativity, that he particularly liked Einstein because they shared pacifist ideals and so on, and that somehow or other this bias led Eddington to negligently throw out some data taken during the experiments because it didn't fit with his presumption or hope that relativity would be proved correct. So I'm going to convince you, I hope, of one important thing, and that is that it wasn't Eddington's decision. So we really need to look at the other people involved. If we're going to maintain this story about bias, we have to talk about some of the other people and what their views were, because as it turns out, Eddington didn't make the most important decisions that are controversial. Then I think I also want to show you that I think they did quite a good job. So let's go on with that. But first of all, we should keep in mind that Eddington was in the minority, right, in being, if he admitted himself, he had some hopes that relativity would be proved correct. Most astronomers at that time were very skeptical or intensely skeptical about general relativity. And of course, as far as the pacifism goes, yes, it's a remarkable fact that both Eddington and Einstein were prominent pacifists who actually publicly opposed the First World War. We should remember that that was a very unpopular position to take. They both risked arrest. during the war. Eddington came quite close to going to jail as a war resister. I think, whatever else we may say, that they can't have had too much expectation of the enormous outpouring of public enthusiasm for their work. And even if the idea of post-war reconciliation did play a role in the public's response to the expedition's news, I don't know that that can really have been anticipated by Einstein and Eddington. Okay, so to make a quick statement, the problem is that Eddington, whose fame is considerable, and Einstein, whose fame is even greater, it tends to obscure everybody else. If you read some accounts, especially popular accounts, you would conclude that Eddington was in charge of both expeditions. He was not. Sometimes you might even get the impression that there was only one expedition, the one that Eddington was on, to the island of Principe. Of course, there was another one. And it turns out that the most important data was taken by the other expedition. So that's why I say that we should be careful in assuming that Eddington did everything. So here are the two men involved. That's Dyson, the Astronomer Royal, on the left. That's Eddington on the right. They were quite close to each other, quite friendly. If Dyson's fame has been eclipsed by Eddington's, it was something he anticipated. He said to his daughter, "If I'm remembered in the future at all, it will be because of my relationship with Eddington." He was very aware that Eddington was this brilliant guy, younger man. Dyson said, "I'll be famous as the guy who was once Eddington's boss, you know, if I'm remembered at all." But it's important for our purposes to note that Dyson was the perfect man to do this job, right? So this job involved differential astrometry, sub-arc second differential astrometry to measure these tiny apparent shifts in position of these stars. That was what Dyson did for a living. He was an expert on stellar parallaxes and proper motions of stars. Sub-arc second differential astrometry was something that he did day to day, week by week in his ordinary life. Eddington actually had quite a lot of experience in that area too, but Dyson was the one who had done this for many, many years. Also, he was the head of the organizing committee. The Joint Permanent Eclipse Committee was a committee under the auspices of the Royal Society and the Royal Astronomical Society to organize all British eclipse expeditions at this time, and Dyson was the chair of that committee. This is the building where they met, Burlington House in London. It's still the home of the Royal Astronomical Society. At this time, it was the home of both societies. So it was Dyson who recognized the importance of 1919 and who decided, okay, the war's still going on, but we ought to try to make preparations to go. This is the track of the eclipse right through the tropical regions of the world. A very unfavorable track. Not only was the timing bad because of World War I, but if you look at this track, you'll see that most of the eclipse, the central part of the eclipse with the greatest duration of totality, is in the mid-ocean. On land, the greatest extent of the track is through the world's two great jungle basins, the Amazon in South America and the Congo in Africa, totally unsuitable for an expedition of this kind. So they really had a very restricted choice of locations. Sobral, a small city in northeastern Brazil, is about the only significant place with really good rail connections, and so that was kind of an easy choice for them. And then the island of Principe off the coast of West Africa was the other choice. The Cambridge team, led by Eddington, went to Principe, and the Greenwich team, led by, or consisting of two astronomers, two assistants of Dyson's at Greenwich, we'll meet them in a moment, went to Sobral. Of course, they were hoping that if one team was clouded out, that the other would be able to get some data. This is the ship that they sailed on. They sailed together because this ship was going all the way to Brazil, but Eddington went as far as the island of Madeira. It's interesting to remember how difficult it all was. This was apparently the first liner to resume service from England to South America after World War I. Had the war, which ended in November 1918, gone on any longer, they would not have been able to go. Even in their own minutes, they mention, well, it doesn't really look like we're going to be able to make it, and then all of a sudden the war ended. Eddington had it even tougher, because between the end of the war and the eclipse, a small civil war broke out in Portugal in January 1919, and when he set out and landed on Madeira, he actually had no idea what ship would take him from Madeira to Principe. He essentially waited a month on Madeira until he found a ship that could take him on. So it was not easy business, even just getting there. These are the two men who went to Sobral, along with Brazilian astronomers who were of great help to the expedition. both expeditions, since they were so lightly manned, I can't help mentioning, even if I run out of time at the end, Eddington had no astronomer with him. He had a clockmaker called Edwin Turner Cottingham. I've often wondered why he didn't take a fellow astronomer. The answer is straightforward. He had 2 assistants at Cambridge, but they both died during the war on active service. So there was nobody left. He took Cottingham with him to have somebody with him to help with the machinery. So they really benefited from a good deal of local assistance. That man, Henrique Moritze, the tallish man there standing beside the 2 men in white, was the director of the National Observatory in Brazil. And the 2 men dressed in white are the 2 astronomers from Greenwich, Charles Davidson on our left, the smaller man, and Andrew Cromlin, an Irish astronomer, standing beside him, still in white. Davidson was in many ways Dyson's man on the spot. He had begun his working life at Greenwich as a computer, right? In those days, there were no electronic computers. A computer was a person, very often a woman, who was hired to do intensive calculations by hand. At Greenwich, they paid better, and so they typically had men working as computers. Davidson was therefore not a university-educated person as far as I know. We don't know a whole lot about him. But he was very trusted by Dyson, especially for his expertise on instruments. And he was the guy who overhauled most of the equipment for the expedition. He was really a man that Dyson trusted implicitly. And that's important because the instrument that Davidson worked did not perform well on the day. And Davidson noted this right away in his diary within a day or 2. And it was eventually Davidson and Dyson who took the decision not to use the data from that instrument. And that decision has later proved somewhat controversial. This picture, incidentally, is of the 2 men with one of the coelostat mirrors used in 1919 when they were preparing for a later eclipse in 1927. This is Andrew Cromlin. He was the astronomer who actually operated the equipment that got the best data on the eclipse. So he actually plays a prominent role. But he was a last-minute substitution. The man who had previous experience of using that equipment was refused permission by the Jesuit order to go on the expedition at the last minute, and Cromlin stepped into the breach. And he was a comet expert, but as a matter of fact, he's the one who got the best data. His instrument performed the best. There's a famous statement by Eddington. He was almost completely clouded out on Principe, but he sent back a telegram, through cloud, hopefully. So the cloud thinned at the very last minute of totality, and the last couple of plates that he took had a literal handful of stars visible, and from that he was able to get some data. But the truth of the matter is, he really needed something else from Sobral. Had Sobral been clouded out, it would have been hard for Eddington to say anything very definitive, certainly about the alleged contest between Newtonian gravity and general relativity. He would have been happy enough, I think, though, to say that he had at least shown that light deflection was a reality. It's remarkable. This is apparently a picture from the estate, the plantation, I should say, I guess, on Principe, where Eddington was located. I'm hoping Vitor is going to come back with some good pictures. I'd be very interested to learn more about it. It turns out they were very close to being totally clouded out in both places. I'm told that this is a picture of the hole in the clouds at Sobral in Brazil that just came into position. This is taken just before totality. You can see the last glimmer of sunlight there, hidden by cloud. That hole just to the right of that bright spot is this hole in the clouds, which is about to park itself over the eclipse so that they could actually see it. So they came very, very close to striking out almost completely, but they got lucky. However, of the 2 instruments that they had with them, and I won't go into it too much today. If you want a blow-by-blow account, you'll have to read the book. But of the 2 instruments they had with them, one did not perform very well. It suffered from astigmatism. They think because the intense sunlight caused a deformation in the coelostat mirror, and that compromised the images. But the other instrument did not suffer from this astigmatism problem. So, of course, in the end, they relied on the data from that instrument. These are the 2 instruments on site at Sobral. The one on the left with an astrographic lens is the one that had the astigmatism problem. The one on the right with the funny square tube was the one that performed much better. I can't resist showing this image. It so happens that during this eclipse there was a remarkably large solar prominence. Eddington got a very good picture. This picture is from Eddington because, of course, the prominence was overexposed on most of their images where they wanted to image stars, but with the cloud that he had, he got rather a good image of the prominence. So that's the picture that we usually see of the eclipse. Okay, I think for this audience, I don't have to worry too much, but let's point out that there were essentially 3 predictions that they felt like they were testing. One is, of course, that perhaps light is not affected by gravity. The other was the original prediction made by Einstein on the basis of the principle of equivalence, the idea that light falls in a gravitational field. If that's the case, then one would expect at the limb of the sun, the maximum possible value of 0.87 seconds of arc deflection. Of course, eventually he developed his full theory with space-time curvature, which adds an additional, essentially doubles the size of the effect to 1.75 seconds of arc at the limb of the sun. The story goes that Eddington, who framed this as being between Newton, if you take the principle of equivalence, but you're still essentially using Newtonian gravity, versus Einstein, wanted somehow to favor Einstein's theory, wanted to demonstrate post-war reconciliation. I have to tell you this anecdote. So you'll recall that Eddington's companion was not a professional scientist. So on the night before they departed England, Dyson and Eddington felt they had to explain to Cottingham what this was all about. So they told him about the 3 possibilities. There might be no deflection. There might be what you might call the half deflection, that's Newton. There might be the full deflection, that would be Einstein. Cottingham got the essential idea, well, the bigger the deflection, the more exciting it was going to be. So he said, well, what if we get twice that? Dyson then said to him, well, in that case, Eddington will go mad and you'll have to come back alone. What did they get? Well, here we go. From Sobral, 2 different instruments. One gets 1.98 seconds of arc effective at the limb of the sun. The other gets quite different, 0.93. And you'll see that one is in agreement with Einstein, but the other within the so-called Newtonian value. And Eddington from Principe reports a value between the 2 possibilities, but definitely quite closer to the general relativity results. So the charge then is that Eddington was biased, but the truth of the matter is it was Dyson who was in charge of the data analysis from Sobral. So if we're worried about the decision as to what to do with the Sobral data, we should really be worried about Dyson. Very quickly, here's a letter from Eddington to Dyson in which he says, I'm very glad to get your news, right? So it's clear from this letter that Eddington was somewhere else while Dyson was doing the data. If you look at the data analysis sheets, it's in Dyson's handwriting, right? So it was Dyson who made the decision. So what was his view? Well, here he is writing to a fellow astronomer saying, the result was contrary to my expectations, okay? And here's Eddington writing to a colleague, this is Eddington with his mother and sister, saying, Dyson was at that time very skeptical about the theory. So at least we can say that Dyson did not share Eddington's bias, alleged bias in favor of relativity. And then another important thing that I want to draw your attention to is that actually Dyson, very briefly in his published papers, but much more in his notes, devotes considerable time to a different analysis of the Sobral, the dubious Sobral plates, which gives quite a different result, 1.52 seconds of arc. What is the difference between the 2 things? Well, essentially, the key part of the data analysis, this is the star field, is that you want to detect the following deflection, a radial deflection outward caused by Einstein's predicted effect, which is, of course, going to be bigger if the star is closer to the sun, like star 2 there, and smaller if the star is far from the sun. But you have to battle against the fact that if there's been a change of magnification between the 2 images that you took, well, then, of course, there'll be a shift in the position of the stars, which is also radial, so it's difficult to separate. But one saving grace is that it will be the reverse. It'll be smaller for stars close and bigger for stars further away. So what he essentially did was to assume that the scale change wasn't that big and see what he got. So when I was visiting the RGO archives years ago, my wife, who's an astronomer, said to me, well, you should ask them about reanalyzing the plates. And when I did ask them, they said, oh, that's already been done. It was done in the 70s. So I went and hunted up the people who did that and looked at their paper. And here's what they got. We'll close with this slide. The left column shows the results from 1919 for the several different instruments. The right column shows the results from the 1917 reanalysis. This is taking the old plates, the original plates, remeasuring them with modern plate measuring machines using modern electronic computers to reduce the data. And you'll see that they agree very closely as regards the 4-inch from Sobral, which is the one that got the good data. And you'll notice that they agree very well with the alternative data analysis method used in 1919. So essentially, they completely vindicated what was done in 1919. They could not do the same for Eddington's plates because they don't survive. We have no idea where they went. Interesting thing is how hard it can be at times to get your story across. So these gentlemen in the 70s did all this hard work. Their paper went completely uncited in the literature. When I found their paper, I could not find a single instance of anyone ever citing this paper. The closest I got was that Stephen Hawking, in his book A Brief History of Time, appears to allude to it, but unfortunately got it backwards and said that he had heard that their results did not vindicate the original people. So they had to write a letter to the observatory pleading with everybody to recognize, no, we said the opposite of that, but it was too late. So I'm going to leave it there, and thank you very much. Between Eddington and Einstein.
What type of contact did they have?
They had no contact at all. Before the war, they weren't really working on similar issues, so they hadn't any particular reason to be to talk to each other. During the war, Eddington did get interested in Einstein's theory, but it's interesting the amount by which communication was severed between the two sides. They did not actually communicate with each other until after the announcement of the eclipse results.
So you gave a kind of very brief description of the two methods of analyzing the Sobral data, the disputed data.
Yes.
So as you said, there are two effects. One is the solar deflection, which decreases as you go further out, and then just an error in the magnification, which will give a deflection that increases. So the correct way to analyze is to include both and fit for both, and then pull out the part due to Einstein. So if I understood you right, the correct answer came when you ignored one of the effects. Is that right?
So
whereas the 79 reanalysis, I presume, included both effects. So I would like to understand a little better.
Yes.
What they did in 1919 and what they did in 79.
Sure. Let me very briefly give you an idea of that. This is an actual page from the 1919 analysis. Those equations at the top showing alpha and E are exactly what we're talking about. Alpha here is Einstein's light deflection effect. E is the scale change. And so they're comparing those for each plate. And what they're doing on this page is actually working out what the average alpha is for these plates. And then here is the 2 pages later is the actual point in Dyson's handwriting where he makes the decision to ignore that data. And the reason that he makes the decision is essentially the following. When they did the first analysis and they extracted both alpha and E, they got a very large value. They got this particular value for alpha, which agreed with Newton, but they got a very large value for the scale change. So the worry is, boy, this instrument had a significant change of magnification between the eclipse and when we took the comparison plate. That's not really supposed to happen. So they did a different analysis, which is the one on this page, in which they said, let's assume that there wasn't a big magnification change, just the minimum predicted by theory. What do we get then? Lo and behold, that's when they get this other result, which agrees in Einstein. So the logic that they put forward was the following. They said, okay, this result, the way we first calculated it, looks like it agrees with Newton, but it also shows that the instrument didn't behave in anything like the way it was supposed to. It had this massive scale change. If we assume that the scale change was small, then we lose the agreement with Newton. So we're unhappy with this data and we're not going to use it. And what's interesting about 1979, when they had No particular problem with their modern equipment. They were able to work it all through. It's more errors in that instrument, but they were able to work it all through. And they actually agree with that alternative result. They say, yeah, the scale change is actually not that big, but you agree with Einstein.
A short question.
In the spirit of giving credit to the unsung heroes,
Yes.
who were the 1979 people?
Yes, thank you. So the most important person, I think, was a man called Harvey, Jeffrey Harvey. I unfortunately took out some of the slides to beat the time. So yes, Jeffrey Harvey was the man who actually wrote the paper that got so roundly ignored. His superior was a man called Andrew Murray, who literally wrote the book on differential astrometry in the 1970s, and he was the head of the astrometry team. And he was the one who actually had the idea, and he's the one I corresponded with and gave me quite a bit of insight into their experience with the data. So they were the two key people involved in the 1979 reanalysis. Thank you.
Okay, so we have to move on, and let's thank the speaker again. Our final speaker for the session is Professor Maria Rodriguez from Utah State University.
Thank you. Present more? Yeah. Thank you very much. Hello. Thank you to the organizers for inviting me to speak today. And it's a pleasure to be back at Harvard. So what I will be discussing today is, I'm a theoretical physicist, so I will be testing some of the ideas of how well actually the shadows that we can compute really probe the event horizon, the geometry that we have behind the computations. And so the main goal here will be to explain these three pictures that you have on your right, where we resolved the problem for the shadows for very specific geometries that I will discuss further. So let me first have a brief introduction, because I think it's a very good time to also remind ourselves where we are in the context of black holes. So yesterday I was walking around Harvard Square, and I was a postdoc here 3.5 years ago, and I was thinking, well, everything looks the same. It felt the same. There was a party in the streets. Everything looked the same for commencement preparations. However, when I went back to the hotel, I started looking at my slides, and I realized that many things had changed in these 3 years. And this is amazing when we think about new events in physics that find new fundamental discoveries. So for me, these are very exciting times for black hole physics. And since my last time visiting here, these were the things we had in hand as measurements. So some Chandra images of black hole jets, as well as the observations for the black hole center in our galaxy. So during these 3 years, there were many other things that appeared, and one was, of course, the LIGO detections of the gravitational waves, and also these new measurements constantly appearing now as became a bit normal or standard for many. But the detections of binary black holes, as well these observations from the galactic center, where we saw that besides the central black hole, we will have sprinkled around it also some black holes of the size of the stellar mass black holes. And more relevant perhaps for my talk, although I'm not involved in the EHT, is just an inspirational image that I will show you now, has to do with the advances in numerical relativity that plays a very central goal, a central role in everything that we are currently measuring. This is the gravitational wave simulations in a stamp in Germany. So all these things happened in 3 years and a half. There was a lot of excitement. And looking at the pictures of ATH for the black hole shadow of M87, I think that, you know, when I was thinking everything has remained unchanged at Harvard, I think many things came up scientifically, so it's an honor to be here at the Black Hole Initiative Center talking today. So what happened is that, prompted by these discoveries, I think also on the theoretical side, we started to think about how we have been handling, or how well can we really describe theoretically phenomena that currently is being observed. And so for that, I'm going to revisit the shadows of a static solution of Einstein's theory of general relativity that has two black holes in it. And this would be a system of two Schwarzschild black holes, and we called that the shadows of the static binary black holes. I also want to show you some exact shadows of the binary system where you can have two Kerr black holes in them, and they will have a very special mathematical artifact, and I will show you those. But this will correspond to the zero temperature, the extremal two extremal Kerr black holes that we can't really do numerically. And then another method that we developed that with these geometries that I will be discussing briefly in more detail, we can also, on our laptops, imitate the full dynamical process and the shadows that are produced in the full dynamical system by doing some quasi-static movements of the orbital spin, imitating the orbital spin of the black hole. So this is what I want to discuss. For this, there will be a few keywords. Most of you are familiar with black hole shadows, but to represent the geometries I will be looking at, I will introduce very briefly what we call the Weyl coordinates, and some of the solutions that are the ones of interest in this case to produce these exact shadows, which are the binary black hole solutions in general relativity to produce then these shadows. And symmetries, we will see, play an essential role in all this story here. So the two talks before were discussing light and how light can tell us more about the geometry. So we know the sun has some rays, and now in general relativity there was this prediction that if we put a massive object, say a black hole, then the light will be bent, and so there will be lensing, and so the observer will actually see the light, and if he doesn't really know what is in between, he will falsely assume that the object is in some other position. So this was something that was discussed within general relativity. And so the propagation of light on curved space-time provides as well a basic probe of the background properties, the geometry now. So this is what we want to study. And the shadows of the black holes are the image of the event horizon, which is lensed by these gravitational fields around the black holes, which is bent around them, and we can superimpose over the background of light. So this is a picture of what we are trying to compute. So here you have a black hole, which is the Schwarzschild black hole, and so this light ray here is one of the null geodesics of the light ray that is the last ray that can escape from the black hole. And so this is the picture on this 2D screen here of what the shadow of the Schwarzschild black hole is. You see in contrast here the size of the event horizon projected on this surface. As well as in this case, you have a Kerr black hole. And in that case, the orbits of the photon orbits are a bit more complicated. And as well, they produce a very special type of shadows for the Kerr black holes. This is one that is highly spinning, so it flattens out on one of the directions. So this is what we are targeting, trying to study the shadows exactly of some solutions. So in this case, what we are going to be studying are the fundamental photon orbits. And so we have, the previous talk was about the discussion of the weak lensing of light. And, but now we are going to be interested more on what we call the strong lensing effects. And they can occur close to compact objects. In particular, ultra-compact objects, and by definition, they're described by spacetimes that have bound photon orbits, dubbed fundamental photon orbits, the FPOs. So this class of spacetimes are and include black holes, but as well you can produce similar effects with very compact objects such as stars, and we will show you I will show you one of these effects in the resolution of the shadows. So for the Schwarzschild black holes, these are planar and circular, so they have a very special name. We call them light rings. And for the Kerr black hole, they are as well spherical photon orbits in addition to the light rings. In particular, for the black holes, this set of FPOs are determined as they determine the edge of the black hole shadow and are unstable. Okay. So in the works, or the story I want to tell today is I teamed up with two of my collaborators in Portugal, Pedro Cunha and Carlos Herdeiro, and so all this is also on a few papers on the archive. So since the shadow is determined by a set of these very special photon orbits, rather than the horizon properties, as we will see, it is possible that different horizon geometries produce similar shadows. So how sensitive is actually the shadow to the details of the horizon geometry? That was one question we were wondering. And so the shadow we know is the fingerprint, so to say, for these black hole spacetimes. And they can actually measure the different properties of the black holes. And so we are interested to see or probe how well these shadows give us details of the geometry behind. So for that, we took a very special kind of solutions, and these are solutions of Einstein's general relativity. They are exact solutions of Einstein's general relativity. They can be static or stationary. First, I will focus on the static cases, and then I will devote some time on the stationary cases, and then contain two black holes. But what happens is when you construct these solutions, they're static, so there's no orbital spin in the solutions. We don't know exactly how to resolve Einstein's equations if it's not numerically for the full dynamical problem with the orbital spin. So the best candidates we have currently are these solutions. And in this case, the two black holes want to collapse and they feel each other. And so in between, there's a mathematical artifact that is a strut. Basically, what you have is a localized conical singularity between them that is massless. And so this is like having a pen between two masses that you want to put together. But this is massless. Okay, and so they solve Einstein's equations, vacuum Einstein's equations, the solutions that I will show you. They're actually zero along every single point in geometry, but in this in the line connecting both, there's a singularity, this conical singularity. So there's a small difference there. So the geometry looks like this. We have to make the problem solvable, and actually Einstein's equations decouple. If we go to what's called the Weyl coordinates, which are rho, z, phi, t coordinates, the problem becomes very much more easier to solve. And the geometry containing two black holes, two Schwarzschild black holes, is of this type. And all the functions u and k take this form here, and you have z and rho as just the coordinates in these functions. And then there are these parameters a, i's, or j's, and k's that show the place where the black holes are sitting basically in space. So in this coordinate system, the two black hole horizons are line segments. Okay, when we move, these are more cylindrical coordinates if we are talking about flat space, but now we have the two masses. So if we are looking at the x, y, z Cartesian coordinates in these Weil coordinates, the black holes are located along the z-axis only. And so you have two rods, that's the jargon of how we represent them. And these A's are just, that you see here in the geometry, are the place or the locations of these edges of those rods. Between the two black holes, we localize the conical singularity that is represented here in a zigzag. So this is a way to represent the two Schwarzschild black hole solutions, which is the exact solution we are interested in. And the other solutions you may know about are the ones in which the conical singularity reaches out to infinity, which corresponds basically to the two accelerating black holes. But for this case, we're going to focus on localizing the conical singularity between the two black holes. And the idea was, well, if we have a conical singularity in the geometry, the question was, does this really affect the shadows of the black holes? So is this the case or not? How well does the shadow probe that we have a conical defect on the geometry? So to do this, I hope everyone is familiar with the way we do the computations, but if not, this is a brief review. So if we have flat space, there's no black hole. What we are going to be taking is a local sky O and a manifold in it, where we defined or colored each of the quadrants with different colors, and in the center we will have just a white dot, meaning light behind the object that we are going to be placing. So numerically, what we're going to be doing is evolving the light rates directly from the light source and detect the ones that reach the observer. So the most efficient procedure is actually to do the inverse. So we are going to reconstruct the light rays and go backwards to produce the shadows. So this is the example that I was showing you in this 3D picture, but now with the background here, you see there's lensing. So here there's a Kerr black hole between this behind screen and us, the observers, and there's a Kerr black hole with this parameters that we place between them. The black hole lenses the background, and the dot here, the white dot, becomes actually this ring, which is basically Einstein's ring. Okay, so this is for the one black hole, and now that we had this way of solving this, we wanted to see what happens with these other geometries. And so we were going to solve the null geodesics problems, and this is what we did for the solutions. So up here, what you have is the two black hole solutions. These are these exact solutions, and we are resolving the null geodesics and studying the FPOs for them. The two black holes are very close to each other. They're aligned here on this axis here, and so you would have to revolve along the axis symmetry to have a 3D perspective of what they're doing. They're very close to each other, so they really look like the shadows of a Schwarzschild black hole. And as we pull them further out to each other, what happens is they start generating lensing as well. But if we're interested as well on the shadows here, and so you can see that there's already some space here which is becoming larger and larger. And so the exact solution, even if we have a conical singularity between them, doesn't spoil the shadow of the black holes. Okay, so this is, again, this is the production of the shadows with the two black hole, Schwarzschild black holes with the conical singularities between them. Okay? So these were the images, and it was kind of interesting to see this because we expected actually to have something that was going to take care or going to show up with the conical singularities. So they appear very similar actually to dynamical problems, and I will discuss that very briefly. And they produce some subtle discontinuity in the geodesic scattering. Basically what happens is the discontinuity shows up very strongly on the lensing effect, but not on the shadows. Okay? As can easily be observed, there's no clear effect on that side. The advantage of doing this with the analytical solutions is that we can very easily as well change the mass ratio of the black holes. So here we started with some mass ratio of 2. In here, the black holes here, this one becomes smaller than this one, as well as here. And here you have 100 as the mass ratio. There's still a black hole here and a larger object in here, and we can still compute the shadows in those cases as well. Another thing we can do is take a different perspective from which we are making the observation. So the observer here lies along a line that is at theta pi over 2, and we can change the observation point and also resolve the shadows of these exact solutions. And as we change the observation point, we see that the lensing effect of the shadows becomes kind of more interesting, and this looks more like a Saturn type of shadow. So what happens at the level of the geometry? I said we had the conical singularity between them. So what is happening, and if we do a true embedding of the geometry now, not the shadows, the conical singularity, as we are going to put them closer together, the black holes, they're more like two balloons that when you put a pen between them, really feel the geometry, the event horizons, do really feel the existence of a conical singularity. However, when we study the shadows, there's no evidence that that is actually showing up. And the reason for that is that there's an additional symmetry in the fundamental photon orbits that we analyzed, because when we have to make the resolution for the shadows, there's a two surface that has that cylindrical topology, and hence it doesn't show the difference. So here this red and blue dots are very close to the conical singularities, and these are the FPOs that you can see traced back and ignore completely what's happening very close to the conical singularities. So there's some geometrical deformation that is physically not visible with the shadows. What we tested as well, we said, well, we could put a star that is larger on the backgrounds of these black holes, and so we took some expression for a star that if it's opaque, here's the star which is larger, and behind we do have a black hole, so the shadows will also feel the presence of these other compact objects as well as for Kerr. And so if the star becomes smaller in radius to the black hole also lying in the geometry, then you will not see the wiggling of the star in that case. So in some sense, the shadow is not really the image directly of the event horizon, but it tells us rather more about the structure of these fundamental photon orbits. At least this is what we are finding. So what we then thought, well, is we want to study whether these probes, these proxies of the solutions with the conical singularities can actually do much more, and and tell us and be used for in comparison to the dynamical problem. And so we found some way of doing that by looking at trying to imitate the dynamical process for those. One option is to study the two Kerr black holes with the conical singularities, and for that there's a new part which is this ergo regions of the two black holes. This is the exact ergo regions for these solutions of the binary black holes solutions. We can also paint the shadows. Here you have the two Kerr black holes, which are highly spinning with the co-rotating spins along this line, and as well we can paint the ones with the counter-rotating ones. Okay. And this is what they look like. Especially, I mentioned the ones that are zero temperature. Those are not feasible to be done numerically. The codes break down, and so these are the shadows of the extreme zero temperature Kerr black holes that, as we put them together, they become a xing-shang. So they're very spiritual as well. So, the last thing I wanted to tell you about is how we could, with these geometries, imitate the dynamical process of having an orbital spin. So I'm a fan of Interstellar, and in there, in one of the papers, Kip was describing how he could move the camera around and look at, capture ideas of the black hole. So we had that idea, could we trace back the null geodesics, and the black holes would be the static or the two rotating ones that don't have any orbital spin. Can we imitate by moving the observer the same effects that the dynamical guys are doing? And so we did this in this way. It becomes more complicated when you're doing things theoretically. So you have a description here in how to consider a map and then tracing it back along the photon positions to rotate. There's more information here. I wasn't going to explain all the details, but it can really imitate what the dynamical process is. This is a video we produced with exact solutions with this quasi-static. So here you see the two shadows that are moving in the background of the Milky Way. This is done on a laptop computer without any dynamical evolution and geodesic solution. And here is the plane comparison with what the dynamical shadows of the black holes were done by Bon et al. On top of that, you can see there's some eyebrows that move. The rotation goes in this direction. The shadows follow. This is our quasi-static black hole. There are differences between this, but if you look at the shadows, basically, there seems to not be any problem in imitating the dynamical by using these ideas of shifting the observer rather the orbits. So let me conclude. So we took a few solutions of Einstein's equations that are problematic. They have conical singularities, but they still seem to produce shadows that are faithful. We computed the exact shadows of extremal black holes and found some underlying cylindrical symmetries that protected us from having any problems with the conical singularities. This was a surprise to us in some sense. And then looking at this quasi-static binary black holes, we found a way, perhaps a more simpler way or method to try to explore what the binary black hole system is doing in this dynamical quasi-static process. So the fun has just begun, so thank you.
So in the case of a real binary black hole, there is perturbation, time-dependent perturbation of the metric that introduces gravitational waves, and you would expect them, if there is a shadow of light coming behind, that the gravitational wave would be perturbations of order unity, when the two black holes are close. So how do you cope with that?
This is for the very slow rotating limit, in which also the shadows were produced in the full dynamical process. So we don't have images, even in the dynamical full resolution of the problem, when there's the ring down, the very fast, and the part that you're saying. So this approximation is an approximation for the very slowly rotating case with the orbits.
Which is like having two black holes separate.
Not really, because I mean they're separately enough, but the shadow, what you call the eyebrows, are following. So there's frame dragging between them. They're not too separated.
Right.
Otherwise
So you're
it would
saying
be-
there is a sweet spot where you don't need to worry about gravitational waves, and you can still do
Exactly.
it reliably.
The eyebrows are the images, this two smaller regions that you see is the effect of the lensing of this black hole against the shadow that shows up here. So each one knows of each other in some sense, right? So they're not far apart that they don't have any effects from knowing that the black holes are there.
Yeah, so you showed the shadow of a star, and the results indicate that if the surface is within the light ring, then the differences with respect to black holes are small. But what are the boundary conditions that you're imposing at the surface? I mean, photons that reach the surface, what happens to them?
Well, there we break the code, right? It's just the surface that limits
So they're
that.
absorbed.
Yeah, they're absorbed after that, yes. Yes.
Time for one more question.
I guess there would be some spin-spin repulsion that would counteract the gravitational attraction and lessen the need for a strut if they're both spinning the same way. But I take it from what you said that you can, is there any limit in which the strut starts to disappear? Or I take it from what you said the answer is there's always a strut?
Well, there should be a limit in which the strut disappears, because this is the limit in which, you know, the dynamical process or the numerical relativists are finding exact solutions without any conical singularities.
No, but I mean just with axisymmetry.
With that, yes, there should be some limit. How we construct them analytically, that's a different story. I don't know currently we know how.
Yeah, so let me just add, there is an exact binary black hole solution without struts.
Yes.
Those are extremely charged black holes.
Charged black holes, yeah. Mm-hmm.
Right, but you can't do the same thing for spin.
No. The spin, in some sense, is very special in comparison with having the two charged black holes that we know exactly and have no struts. Yeah.
Okay, so we'll have to wrap up. Let's thank the speaker first of all.
Thank you.
And so we have a coffee break now for 20 minutes. I'd like to thank all the speakers once again for very nice talks and also for keeping on time very well.
I hope everyone have a nice break. Now we have our second session today. Our first speaker, before that, I would remind everybody again that please leave your question to the end of the talk, unless you have something like obviously short question for a quick clarification. Otherwise, please leave the question at the end. So we'll welcome our first speaker, Priya Natarajan, and she's going to tell us about black hole archaeologies, tracing the origin of early seed black holes.
Hi, everyone. It's a real pleasure and privilege to have this opportunity to present the work that me and my research group have been doing for the last couple of years on the idea of black hole seeds, looking into the problem of the origin and properties of black hole seeds. So first I wanted to thank and give a special shout out to two collaborators, my graduate student Angelo Riccardi, who is in the audience, and Fabio Pacucci, who was a postdoc at Yale till recently. And a lot of the results that I will be showing you form a substantial portion of Angelo's PhD thesis. And I've listed here also a cast of characters, people who've been working very actively over the last decade or so on trying to understand the origin of the first black holes, using a variety of approaches, modeling, simulations, and so on. So the origin and the properties of black hole seeds that grow to produce the detected population of accreting supermassive black holes, quasars, are really unconstrained at the moment. And it's very much like the challenge that we have in archaeology, where we see the remains today and we need to reconstruct what a monument, in this case, this is the Temple of Hera, might have looked like in the past. So the issue is that actively growing black holes, which we end up seeing as quasars, are not directly observable even now at the earliest epochs when the seeds are actually forming. And therefore, discriminating between various models to describe the origin, the initial mass functions of these seed black holes is very, very challenging. But we have a new set of observables, and I'm going to show you this range of observables at low and high redshift that offer very exciting prospects for nailing down and hopefully unraveling the true nature of these black hole seeds. So one of the key challenges, as you may imagine, lies in the complexity of the problem, the intermingling of the physical scales and temporal scales that characterize the growth of black holes over cosmic time, as well as the disentangling of the confounding effects of the initial conditions, the seed mass function, the accretion physics that you need to actually grow this population of early black holes, and the actual dynamics of the mergers of black holes. And the reason for that is we know that black holes likely grow in 3 different modes: direct accretion of gas, actual mergers with other black holes, as well as accretion episodes, perhaps bursty episodes, that are triggered when during mergers of dark matter halos and galaxies and their black holes. So this is a brief outline of what I want to cover today. So give you a little bit of motivation for why we are examining multiple seed formation scenarios. So obviously the motivation is observational. And then I will outline the channels that we currently have for producing 2 broad classes of seeds, light and massive initial seeds. And then, of course, the meat is to see how you can map these seed formation scenarios to high and low redshift observational predictions that you can then test with data, either data that we'll have in hand very soon over a range of wavelengths. So this is sort of multi-messenger data sets. So with JWST, LISA, and any potential high-resolution, high-sensitivity X-ray mission like LINX. And then I want to close with sort of a brand new idea that I've just started working on with Google X. Okay, so we detect, as you all know, luminous quasars throughout cosmic time. Let me see if I can get the... Yeah. So through cosmic time, and obviously it's very interesting and important to understand the origin of the earliest black holes from which you kind of grow this population. And the seeding problem, interest in the seeding problem, particularly now, is also driven by the fact that we are starting to discover this population of very, very massive, supermassive black holes already in place very, very early on in the universe. So with the detection of luminous, very luminous quasars from redshift of about 5.5 to 7.5, we now have not just freak objects, but what appears to be a population. So the very bright end of what might be a large underlying population. And what is problematic at the moment is that the masses inferred for these accreting black holes from their luminosities suggest that they may be between 10 to the 8, 10 to the 9, perhaps even 10 to the 10 solar masses already at these epochs when the universe is just a fraction of its current age. So what this all suggests in recent modeling work that's been sort of pursued to sort of put together this accretion history of black holes is that perhaps to describe the growth of the most massive black holes, not just at the earliest epochs, but at all later epochs, it looks like there's some new elements that are required in the modeling. And you might say, why is that? So the reason for that can be seen rather simply here. So what you see here is the masses of initial black hole seeds, and this is the efficiency of accretion to end up with a final black hole mass, a putative mass of 5 billion solar masses by, say, redshift 7. So what you find is that in order to end up with something that's 10 to the 9 solar masses by redshift 7, if you start with a very light seed, you really have to be well super Eddington, accreting steadily super Eddington for a large fraction of the time, if not for the entire time since the seed was formed, in order to explain this final mass. Obviously, the constraint gets to be a lot less stringent if we want to reach this final mass at later times. So the question is, of course, Ramesh and his collaborators will tell you that GR-MHD simulations are now telling us that super Eddington accretion is not a problem. But the issue is in the larger cosmological context. So those are simulations that are done on very, very small scales. And as I mentioned, one of the challenges in the black hole growth problem is the coupling of scales. So we don't actually know whether cosmologically we can arrange the circumstances in the large-scale gas flow to actually have sustained super Eddington growth for the entire time if you start out with very low mass seeds for these supermassive black holes that you are seeing at high redshift. So let me briefly outline some of the challenges in this problem and how we've actually dealt with it. So what we've really wanted is a coupled understanding, not just of the inner regions, the innermost regions up to, say, 10 to the 5 Schwarzschild radii or so are not directly observationally accessible, bar, of course, the recent silhouette of M87 that the Event Horizon collaboration has provided us. But what we really need to build a composite model is to connect the larger scale environment of the accreting black hole to the growth of the black hole to the assembly of the stellar component. And I'll show you what the motivation for that is in just a minute. And so what we need is to incorporate the large-scale structure framework, so cosmological simulations in the context of the lambda CDM model is what I'll be talking about. And then we need to start with an initial set of seeds, have some ideas, models for seed formation, and then also some kind of idealized simulations for early growth, because we can't quite couple all these scales in a single simulation quite yet. And so then the big unknown is accretion physics. So we have some guidance from simulations, but the guidance that we have is on very small scales. And we again need to patch on to intermediate scales what these accretion models might look like. In fact, what is really important is not just the accretion models, but the feedback, the coupling of the energy to the gas in the inner regions of, and how energy and momentum are actually transferred in the inner regions. And of course, the final kind of fly in the ointment is the merging dynamics, the detailed dynamics of how two black holes actually merge, how long it actually takes for them. Of course, we know all these processes. We know that stellar dynamics can grind them in closer, and the presence of gas can also pull them in. So in the approach that many of us in the field have adopted over the years, we start out with the larger context of dark matter, and then we try to track the co-evolution of the black hole and the stellar component. So the joint assembly history of both the stars and the black hole over cosmic time. And as I said, the challenge has really been sort of a mismatch of scales, if you will, where we have very tight observational constraints and where we have some insights from detailed modeling, but there's a lot of interpolation that needs to be done. So there are many coming directly now to the various channels for making seeds. There are many physically plausible and permissible ways to make seeds in lambda CDM. So one of the standard mechanisms has been sort of expected that when you make the first population of stars, you will have some remnants, the remnants of those first stars, and we know the IMF there is skewed to a high mass end. So you'll end up with sort of these remnants that are maybe between 10 to a few hundred solar masses. As I mentioned, for the early behemoths, these quasars at redshift 6-ish and 7-ish that have very, very massive black holes already in place, we have postulated, many groups over the years have been contemplating the possibility of making very, very massive seeds from the get-go, very early on. So several channels have been proposed. One is you start out with nuclear star clusters, and you have the coalescence of these individual remnants that can then build up to about 10 to the 3, 10 to the 4. Or slightly more radical idea where basically you have direct collapse of pristine gas that can then give you a seed that's between 10 to the 4 and 10 to the 6 solar masses. Of course, there are uncertainties in all these channels, and there are some specific conditions. For example, for direct collapse, as we'll just see, we need some very specific conditions to effect direct collapse and to form this sort of massive seed. But interestingly, what we find is these conditions are not punitive. They're actually available in cosmological simulations. So in fact, it's quite feasible in the early universe. There are sites. And remember, to account for these rare objects at very high redshift, we need a seed mechanism, a mechanism to make massive seeds that doesn't have to be incredibly efficient because we have to explain just the rare population, as I mentioned. As I mentioned, massive seeds appear to be needed, that channel appears to be needed to explain the very bright end of the luminosity function of quasars, not only at very high redshift, but to simultaneously fit the very massive end of the black hole population at all epochs. It looks like massive seeds alleviate the problem. So let's take a peek into what we know about the population 3 channel. So this is one of the best determined IMFs, the initial mass function of population 3 stars that was derived by Hirano and collaborators recently. And what you find is the stars themselves range in mass from about 10 to a few hundred solar masses. So we can expect light seeds of the order of 10 to 100 solar masses to be the result of POP3 formation. However, there's a little bit of a conundrum here. So in simulations where people have been able to follow on this population of remnant black holes that result from population 3 stars, they find, so these are adaptive mesh refinement simulations, so what they find is these seeds are actually quite stagnant and they don't grow robustly. And they actually grow very, very laggardly at early times. So if we are looking for this channel to be the way to describe the supermassive black holes that power these high redshift quasars, this ain't working. So this is really, really quite hard to pull off. And of course, as I said, there are ways to actually superboost, start with these light seeds and to superboost their growth at very early times. So one model that we suggested a few years ago was an early amplification of, you start off with a light seed, so you have a wandering stellar mass black hole in a dense nuclear star cluster that is fed by cold streams of gas. And it's the random motion of this black hole within this inner core region, a very gas-rich region where the opacity, the tau, the optical depth is actually about 0.8 or so. You find that what you can do under these circumstances is you can prevent the formation of an accretion disk, and basically you have this sort of wind-fed accretion solution, so you can have very rapid supra-exponential mass growth. And what you find in this kind of amplifier, early nuclear star clusters, you can start with a seed that's about 10 solar masses, and very rapidly, within a saltpeter time, within about 10 to the 7 years, you can amplify the mass to about 10 to the 4 solar masses. So, and of course, you have this direct collapse channel that I talked about earlier, where essentially you have the direct collapse of pristine gas that forms a massive pre-galactic disk that then goes unstable with some non-axisymmetric perturbations, maybe bars within bars in the center. And then you shovel mass in very, very rapidly, and you shred angular momentum very rapidly with the bars, and you end up with a very, very compact, dense object, which we believe is inevitably going to form a black hole. So at the moment in simulations, we can resolve up to certain earlier stages of this process, and what we find is that you can assemble these very massive pre-galactic disks in these pristine halos. So the reason we want the halos to be pristine is, remember, we want this gas to directly collapse, not cool, not fragment, and not form stars. Instead, we want it to collapse and make its way to the center. And so when you look at what are the kinds of sites in the universe where this can happen, it turns out that preferentially low angular momentum dark matter halos from the low spin distribution and are probably the most viable sites. So there's one reason why I really like this particular model is the initial conditions for the seed formation already set up a correlation between the larger scale environment, the properties of the dark matter halo, and the black hole mass. And as you all know, and as Changpei mentioned, the M sigma relation that we measure at redshift 0, it's an open question whether it's correlation and what is the causation. So we don't quite know what it is, right? And people like me have been working for more than a decade trying to unravel whether it's a mere correlation that has to do with the quirks of the assembly history and merging history of dark matter halos in which these black holes are placed, or it reflects a fundamental physical causation, a process that is set up very early in the initial conditions. So this model allows you to test that possibility of setting up an initial correlation and then seeing how that evolves over time to see if you can explain the M sigma that you see. So this is a set of simulations, once again, from Hirano and collaborators, where they're actually showing that you can have direct collapse proceed in a bunch of different ways. You may not necessarily have a pre-galactic disk assemble, but what you can have is you can have a very supermassive star that finally collapses directly into a black hole. So anyway, the bottom line is that you can make massive seeds that are about 10 to the 4 to 10 to the 6 solar masses very, very rapidly. So now, in order to understand, if you have these, say, two largely distinct modes of seed formation downstream at late times, how do we discriminate between them, given that accretion physics, dynamics will scramble the initial conditions, right? So, but before we do that, we need to propagate these models to couple them with an initial seed mass function with some kind of accretion physics to see what kind of electromagnetic radiation you could get out of them, to see what we can predict. So to kind of bracket the possibilities of our uncertainties, current uncertainties in our knowledge of accretion physics, we sort of bracket two modes. So you have a thin disk accretion mode, the familiar sort of alpha disk case, where this mode is really feedback limited. It has inefficient growth, but it has very high radiative efficiency. So this is sort of Eddington limited. And so the other possibility is slim disk accretion mode, which is basically you're essentially limited by the gas supply, so you can assemble a huge amount of mass very, very rapidly. It has very low radiative efficiency, and you can get super Eddington accretion rate. So we are bracketing the possibilities of sort of Eddington limited growth and permitting super Eddington growth. So these are sort of the two broad kind of brackets in terms of our uncertainties for accretion physics. So what we really want to do is to take a template massive seed, a template light seed, and then look at how the early growth would be mediated in these two modes and to see what kind of observational predictions we could potentially make. So what we find, so this is work that was done with Kwang Ho Park as well as with Fabio Pacucci, that what we find is the growth is really jump-started for larger initial black hole seed masses because the criterion that jump-starts more efficient growth has to do with the gas mass in the inner regions and the gas density in the inner regions. And since the massive seeds tend to form in the rarer, denser halos, they have a head start in growth. Even after having an initial high mass, they have a head start even in the growth. So you might say, okay, how do we discriminate? So it turns out that for direct collapse black hole seeds, there is an interesting sweet spot. So as I mentioned, there are some particular conditions that are required to form these massive seeds. So one of them is that you need a pristine atomic cooling halo, because you want to prevent cooling and fragmentation and star formation. You want direct collapse. So one way to do that is to have an external source of radiation, say some UV photons, the Lyman-Werner photons from a nearby galaxy, star-forming galaxy. And why do we need that? To basically disassociate any molecular hydrogen that might form, because as you all know, molecular hydrogen is a much more effective coolant. So if you want to suppress cooling and fragmentation, you better make sure that you retain this as an atomic cooling halo while you directly collapse to form a massive seed. So, but one interesting consequence of that is that if you go and look in cosmological simulations, what are the kinds of sites? So this would be a galaxy that has a POP3 cluster that's just formed. Then the most opportune site for forming the massive seed is a satellite halo that is nearby. So of course, this satellite will merge very rapidly with the parent halo, and for a transient period of time, you have a very peculiar object, an object with very interesting discernible properties. And that is, you will have a galaxy in which the black hole mass exceeds the mass of the stellar population, completely the converse of what we find by redshift 0. And this, at this stage, not only is the mass of the black hole dominating over the stellar population, the accretion onto the black hole will also dominate the overall luminosity of this object. So we've called this object rather unimaginatively, I might add, as obese black hole galaxy. So in contrast, if you start out with population 3 seed remnant, you do not have this sort of inversion. So, and this is again, I want to keep coming back to the fact that this is again very interesting, because at early times at seeding, whether you start with light seeds or massive seeds, when you have this very interesting stage of an OBG, you eventually have to journey over cosmic time to end up where we are for M sigma today, where the mass of the black hole is really tiny. It's only 1,000th of the mass of the stars in the inner region. So not only are there interesting signatures of seeding that you will find in the journey, which I won't go into today, but I'm going to focus on this place, sort of this epoch, redshift 9 to 10, where you're likely to see a very, very strong, distinct signature. So these are predictions for the spectra of these peculiar objects for these OBGs. So remember, the configuration is you have a massive black hole seed that is growing copiously, and it has merged with the parent halo with stars. So there's a small stellar component as well, whose mass is small compared to that of the black hole. And so what you find when you do when you track the early growth of this configuration, both aging the stellar population and the growth of the black hole consistently, you predict that much of the radiation, fortunately for us, will be moved from the X-ray, will be reprocessed into the infrared. And so these are the predicted spectra. So this is for a classic OBG that ends up being about 10 to the black hole mass itself is about 10 to the 7th solar masses by redshift 9. And you see there's a very distinct shape that is predicted, spectral shape, that will allow it to be discriminated from other usual sort of old, dusty, dead populations. So you have extreme emission line galaxies, dusty galaxies, and you find, however, that this nice slope between 1 and 3 microns will allow you to sift out these candidates. And what you see here in black are the NIRI and MERCAM instrument bands on the James Webb Space Telescope. So I think you can, by eye, you can see that these obese black hole galaxies will be booming. They'll be extremely bright, and that should be detectable. And whereas if you look at the similar configuration for a light seed, where you have a population 3 seed remnant, and the stellar population, and you co-evolve them once again, and you compute what the spectral output looks like, we predict that flux is going to be well below the MIRI and NIRCam sensitivities. So population 3 seed light seeding model black holes that are even actively accreting at early times, at epochs about 9 to 10, are really not going to be detectable. So we've sort of stuck our neck out and said that if JWST detects any sources at all, they are likely to have been powered by massive seeds. And of course, you might ask, how is JWST? I've told you these are rare objects, so how is JW going to find them? They will have to be pre-selected, and we can pre-select them from current deep data sets combining HST, Spitzer, and Chandra data. And Fabio Pacucci and other collaborators have shown that in the Chandra Field South data at the moment, there are a handful of candidates, a small number of candidates. So these would be pointed JW observations, not in the survey mode. So now let me move on to the more sort of potent, more potent set of observational predictions for the population of growing black holes. So as I said, so these are sort of the ingredients of the modeling, the forward modeling, where you start with initial seeds, you propagate forward to make predictions for various redshifts starting from 6, 3, 2, 1, and 0. So once again, you start with the seeding models. And so here is an example of 2 kinds of accretion models just to show you the results. As I said, there's a parameter space, and we've done an fairly exhaustive exploration of that in a set of papers that was published last year. So here we're showing sort of 2 models where black hole accretion is sort of tied to the star formation. So this is again a model driven by empirical evidence that the black hole growth and stellar assembly are very intricately linked. And the other is also an observationally determined accretion mode, where basically you draw from the Eddington ratio distribution derived from the luminosity functions of X-ray AGN. So then, of course, as I mentioned earlier, part of the biggest uncertainty is in the merger dynamics. How long does it actually take? So we know that dark matter halos merge, structure builds up hierarchically in a lambda CDM universe, the galaxies merge, and the black holes that they host in their nuclei also have to merge, except the time, how long that actually takes, is something that we don't know. So we start out, again, bracketing the cases with a probability that's a low probability, about 10%, that every merger will lead to a black hole merger, and a very optimistic case. So now I'll just show you very quickly where some of the discrimination for seed models arises from. So the key discriminant, these are predictions for high redshift luminosity functions. So for a telescope like the Lynx telescope, for example, which is much more sensitive than Chandra. So the high redshift, high luminosity end, so the purple and the green are sort of the massive seed models. And you find that that's very sensitive to the maximum seed mass. Whereas the low luminosity end is very sensitive to the abundance of seeds, right? So these are the 2 big uncertainties for the initial mass function that we, for seeds, that we don't actually know. So it turns out that you might think there could be no signature at low redshift, but it turns out that there is an interesting signature, which is the local occupation fraction. So if you look at galaxies that host a central black hole, so 3 times 10 to the 5 or more massive as a function of their stellar mass. So these, the black dots are data from the field and from a cluster from Virgo data from Jenny Green and Elena Gallo and others. And what you see in blue are our model model predictions for the various seed models, light and heavy, and the accretion prescriptions. And the triangles here show you a prediction from N-body simulations from Michael Trammell and Sharma and others from the Romulus suite. So the key discriminant, of course, is going to come from gravitational wave signatures. And that is because the seeding signature is independent of accretion, where we are going to be just counting merger events. Of course, what we don't know is the timing, and therefore the overall abundance of these events, right, is a bit uncertain because we don't know how frequently you will affect the final mergers. So as I mentioned, we do sort of, again, bracket two possibilities. There's a pessimistic where the merging probability is only 10%, and an optimistic case. And here you see that you get real discrimination between the light models, which are shown in orange and yellow, and the massive seed models that are shown in green and purple. So you find that at low chirp masses, so this is chirp masses, so for low chirp masses, you find many more events that are driven by light seeds compared to massive seeds, whereas at high chirp masses, you see a drop-off in light seed events because this is the initial mass function of direct collapse black hole seeds. That's what you start getting access to. So there's one other kind of new possible way for detecting. So far I've talked about how we can use actively growing black holes at high redshift to constrain these models. So about 20 years ago, we predicted that you could have some Sunyaev-Zeldovich decrements, both kinematic and thermal decrements that come from quasar outflows that are long-lived, that live well beyond the quasar lifetime. So they'll be lingering, and if they were detected, they would give us access to inactive black holes at high redshift, because the Sunyaev-Zeldovich effect is independent of the decrement, is independent of the redshift. So the first one was just found, and I just heard that a few more have been recently found. So it's a very promising way. So I'll just wrap up here with this final new exciting project that I've just started with help from Google X. So as I mentioned, part of this model building exercise that we have been all indulging in over the years has to do with the fact that in the black hole growth problem, we know the causal relationships. We have a set of physical laws that tell you how black holes grow, how structure assembles, and so on and so forth. And for those of you who are following the literature in machine learning and AI, some of the biggest challenges right now for them are separating out correlations from causations. And so our problem in astrophysics is a wonderful template that will help sift the correlations from causation. So what we are doing is we are assembling a multi-wavelength observational data set that combines black hole data that we have from HST, Chandra, Spitzer, all the databases, and the published databases of papers that have made measurements and report measurements, as well as simulation outputs of these various simulations that I've shown you that are producing slices at various redshifts. And the idea is that we could combine and have a new search interface that we are in the process of developing that would allow for you to retrieve new kinds of correlations where in this event we know the causative vectors, right? So I'll just stop here and thank you for your attention.
So I guess due to interest of time, any one quick question? Go ahead, Abby.
So in your models, what would be the highest redshift that you would expect any detection with any of the techniques that you alluded to, so that if we do detect a black hole above this redshift using gravitational waves or JWST or whatever, it would be a violation of Gaussianity, let's say, for the standard cosmological model, density perturbations.
Right. So I haven't really worked out the exact number for violation of Gaussianity, but what I can say is that even if we detect a single such candidate supermassive black hole, 10 to the 9, 10 to the 10 solar masses at redshift 9 or 10, that, or even, a small population, a handful of them, say a handful of lensed ones or JWST candidates, then we can already start putting a constraint on the maximum seed mass that you need to have. So what that can give you, it'll give you a constraint on the tilt of the initial mass function of black holes, which we can then use further to say something about the deviation from Gaussianity for the underlying dark matter field.
Okay, thanks, Priya. And let's welcome our second speaker, Stefano Aretakis, and he's going to tell us about the observational signature for extremal black holes.
Okay, thank you. It's my great pleasure to be here. I would like to thank the organizers, and in particular Professor Strominger, for the invitation. I'll talk about some work on extremal black holes, which is joined with Yannis Angelopoulos, who is at UCLA, and Diane Geitz, who is at Cambridge in the UK. So I'm a pure mathematician, so my first priority is to prove theorems in a mathematically rigorous way. And my second priority is to try to address questions that are of some physical relevance and importance. So what is one such question? One such question is if there is an observational signature for extremal black holes. That is to say, if there is a distinguished feature in the dynamics of extremal black holes that can tell us that the perturbed black hole is an extremal one. So we would like to see if we don't know whether a black hole is extremal or not, but we have some information about their dynamics, if we can conclude that the black hole is extremal or not. So that's what I mean by observational signature. And more specifically, we would like to see if such a distinguished feature can be measured from functional infinity. So before I go into the details of this work, let me briefly explain why one could possibly be interested in extremal black holes. So from a theoretical point of view, extremal black holes correspond to maximally rotating black holes or maximally charged. One could think that these are non-generic black holes, precisely because of this property. But on the other hand, just because they're non-generic doesn't mean that they're not real. So it's studying their dynamics that makes them more relevant from a physics point of view, and that's exactly what we want to do. They also have various interesting properties, like uniqueness properties. They saturate geometric inequalities that contain the mass, the angular momentum, etc. They find applications in theoretical physics. There have also been works probing electromagnetic and gravitational signatures, which are different from the ones that I will present today. And also, their nonlinear dynamics have some turbulent gravitational behavior. So there are quite interesting properties in the theoretical side. In the more practical side, there is a vast literature in astronomy that suggests that near-extremal black holes might exist. I'm not sure if this literature is correct or not, but at least it exists. So near-extremal black holes at least seem to be relevant. The astronomical evidence that I refer here is mostly based on X-ray observations, but very recently a group at Princeton suggested that highly spinning black holes exist already in the data, in the observations of advanced LIGO. Okay. Oops. The pictures are not very nice here, I don't know why. Okay, so what is the problem? As I said, the problem is to understand the dynamics of black holes. So I will consider here, for simplicity, a model problem. So I will not study true gravitational perturbations, but I will study the simplest kind of perturbations, namely scalar linear perturbations. So I don't know why the picture doesn't appear. So this is the event horizon. This is null infinity. This is the initial hypersurface. We will consider initial data for a scalar perturbation on an initial hypersurface, and we will try to see how the perturbation evolves in the future. That's our problem. And we will additionally assume that the perturbation is supported near the event horizon here. So I will not assume that the black hole is extremal. I will just assume that I have this picture, I have the exterior of the black hole, I consider a scalar perturbation, and I will assume that I know the scalar perturbation. So what I would like to do next is, if knowing the perturbation of the black hole can allow me to conclude that the black hole itself is extremal or not. That's the main topic of this talk. Now, since, as I said, I would like to assume that the perturbation is local, so it's initially only near the event horizon, and since I only want to study classical general relativity, so no quantum effects, of course I have to respect the domain of dependence, which means that the perturbation will only propagate in this region here. And the more localized the perturbation is, the more localized this region will be, just by the domain of dependence. So if you would like to study the effects of this perturbation on null infinity, then clearly you will need to go at very late times on null infinity. That's the only way you can see the perturbation. So our study will involve asymptotics of the perturbation on null infinity. By this I mean I will study the behavior of the gravitational field, of the scalar field, at late times on null infinity. Why do I care about null infinity? Because of the very simple reason that, okay, if we are on Earth and we're measuring the scalar perturbation at Earth, then the leading order approximation to this is the radiation field at null infinity over R plus lower order terms. So the scalar perturbation, of course, vanishes at null infinity because null infinity is at infinite radial distance. But the radiation field, which is the scalar perturbation times R, where R is the radius, it's somehow the distance from the center, is finite. And this expression here is called the radiation field. If we divide it by the distance at the Earth, then we get an approximation for the perturbation itself. Okay, so in other words, we assume that we are observers observing a black hole, and we model that we observe from future null infinity. All right, so here is the main result of my talk. As I said, we will consider the... Okay, as I said, we will consider that we have a scalar perturbation of a black hole. And the only information that I know is that this black hole is a Rieser-Nordström. I don't know if it's extremal or sub-extremal, but I know that the black hole is Rieser-Nordström. So this is the simplest kind of black holes, and that's why I consider this. It's convenient mathematically. So I will assume that I can measure the radiation field at null infinity, and nothing else. And also the mass of the black hole. So I will assume that I know these two things. Then we form this expression here, which purely depends on the mass of the black hole, and as I said, the radiation field. So the radiation field decays in time. I appropriately rescale it to get a limit here in time, which is non-zero. So this factor here is appropriate so that this limit is non-zero. This is a limit in time along null infinity. And this is consistent with what I told you here, that if your perturbation is very localized initially, then you will need to observe at very late times on null infinity so that you can have something meaningful. So this is the late time behavior of the radiation field on null infinity, and this is the integral of the radiation field on null infinity. and I take the sum of these two expressions. So again, this expression is 100% dependent on the radiation field and nothing else. So here is the result. If you compute this expression at null infinity, and you find that the answer is non-zero, so this number here is a non-zero number, then the black hole is extremal. If the black hole is sub-extremal, then this number is 0. So if you make a measurement null infinity and you find that this number is 1, then you can immediately conclude that your black hole is extremal. If it goes sub-extremal, then this number will always be 0. And for generic scalar perturbations, this number in the extremal case is non-zero. Okay, so we have examples where it's non-zero, and if it's non-zero, then it must necessarily be extremal. So this expression here is what we call an observation signature for black holes. It's an expression that distinguishes extremality from sub-extremality. And it's an expression that can be computed in the observation zone, namely null infinity. Okay, that is the result. How would you prove this result? So, as I said, for horizon localized perturbations to register null infinity, we will need measurements of null infinity at very late times, just by the domain of dependence property. So, in other words, in order to prove these results, we need to derive precise late time asymptotics for perturbations on null infinity. And in particular, we need to see the power law tails, the price law tails. So in particular, we need to go beyond the quasi-normal modes. So we need the quasi-normal modes to die, then we have the power law tails, and it's these power law tails that will produce the result that I showed you. Before I give you more mathematical details about this, let me show you if this result here can be confirmed numerically. So indeed, Khanna at Dartmouth was able to use his supercomputer resources to numerically confirm this result. So what did they do? They considered again a Rising-Nordstrom space-time. They considered this truncated version of the signature that I showed you earlier. So in other words, instead of taking the limit at infinite time, they just take this expression at some fixed time, and instead of taking the integral from time 0 to infinity, they take the integral from time 0 to time t. So it's a truncated version of the signature that I showed you earlier. The limit as t goes to infinity of this expression gives us the signature that I showed you in the previous slide. So it's exactly here. So what they were able to do is they were able to plot this function of time at null infinity numerically. So in the sub-extremal case, for example, in the sub-extremal case, here is the plot of the logarithm of this expression. And as we see, after some time, you have here the quasi-normal modes, and once they die, then this expression, the logarithm of this expression goes to negative infinity, which means that this expression goes to 0. So this is a numerical confirmation that this expression goes to 0, so the signature is 0 for sub-extremal black holes. On the other hand, if you consider an extremal black hole, and you consider the same expression, S of psi, then for some time, it's about 100 masses time, which is the period during which the quasi-normal modes are excited. After this time, then you have that your signature tends to a number which is non-zero. 0 is here. So the plot confirms that this result is true. As I said, mathematically it's convenient to consider Rising-Nordstrom black holes, but of course the astrophysically relevant black holes are the Kerr black holes. So the main motivation of Khanna and his collaborators was to study Kerr and specifically extremal Kerr. So they considered exactly the same signature, slightly appropriately modified, so that it accounts for extremal family, not the Rising-Nordstrom family. And they concluded that numerically that indeed this signature also applies to the extremal Kerr case. So you have the signature here, and as time progresses along line infinity, this function tends to a number which is non-zero. Whereas in the sub-extremal Kerr case, the function s, so this blue thing, would go to 0. I want to emphasize here that there is an exact breakdown, like a sharp breakdown. Sorry, let me go back. This number here in the sub-extremal case is always zero, no matter how close to extremality you are. But in the extremal case, it jumps, and it gives you non-zero numbers. So it's really a number that sees the exact extremality at null infinity from the dynamics of the black hole. Of course, now, if one is interested in not exactly extremal black holes, but near extremal black holes, which are more astrophysically relevant, then one would need to study an interpolation between the two scenarios and find a transient signature. And in the work of Khanna, they can also find this transient behavior of this signature. And this work has not been published yet, but will be published, I believe, this week, the numerical work. Okay, that was the result that I wanted to present to you. What I would like to spend the next few minutes is to show you what is the physical meaning of that signature that tells us if the black hole is extremal or not. So, let's start with the sub-extremal case first. The study of this problem, scalar, linear, gravitational, electromagnetic perturbations on black holes, is an extremely active area in mathematics, in particular, and has many contributors in the past decade. It was impossible for me to even list them, so I will not try to do it. Instead, what I will show you is just a theorem that gives you the asymptotics, the precise late-time asymptotics for scalar perturbations on a Rising-Nordstrom background. So, if we have a solution to the wave equation on sub-extremal Rising-Nordstrom background, then along the event horizon, H is the event horizon, along the event horizon, the scalar perturbation, to top order in time, behaves like 1 over time to the 3, so the decay rate is 3, times this factor here, 8 times H1. Same exact asymptotic, leading asymptotic term for hypersurfaces away from the event horizon, but of constant radius, and a slightly modified expression for the asymptotics of the radiation field on null infinity. So these are the asymptotics of the scalar perturbation and the radiation field at very late times on a sub-extremal Rising-Nordstrom. This expression here, this constant here, the asymptotic constant that appears in the top order asymptotic term in the time expansion, is given in terms of the initial data by this expression here. This is on time equals 0 hypersurface, is an integral on the time equals 0 hypersurface, and an integral on the bifurcation sphere. And this expression is finite for smooth initial data, and is generically non-zero. Okay. So as a comment here, we can also produce, if we assume that the scalar perturbation is supported on angular modes, then we can produce a 2L plus 3 asymptotics. Whereas here you only see 3 decay rate. Now, this constant I1, of course, plays a fundamental role because this is exactly what generates your precise asymptotics. It's given by this expression on the hypersurface time equals 0, but it can also be given as an expression on null infinity. So if you know the radiation field on null infinity and you take its integral, that's it, nothing else, we multiply it with the mass, okay? Then you get this constant that appears in the asymptotic expansion of the scalar field everywhere on the event horizon, a constant radius, and null infinity. Okay, so this constant here is at the same time a constant, it's the integral of the radiation field. So what does this tell us? That tells us that if we appropriately rescale our radiation field, like if we take the limits of the radiation field or on constant T R hypersurfaces or on the event horizon, then these limits, precisely because of the asymptotics that I showed you earlier, are given by this constant I1, which is nothing else but the integral of the radiation field. So in other words, the asymptotic behavior of the scalar perturbation on a sub-extremal background is completely determined by the integral of the radiation field on L infinity. And this is what is known in physics, that late-time asymptotics are dictated by the weak field dynamics. These are the late-time asymptotics, and these are the weak field dynamics. These are the dynamics on L infinity. So late-time asymptotics everywhere in space-time are given by weak field dynamics. And again, this is in the sub-extremal case. This result here, in particular, the first one, is the result. So if you bring this term to the left, then you have to the right, you get 0, and you get this result. Okay. So that shows you that in any sub-extremal black hole, the signature is always 0. All right, now everything I said so far was about sub-extremal black holes. What about the extremal ones? All right, so again the picture. So in the extremal case, things are slightly different in the sense that on the event horizon, we have a conservation law, which is not present in the sub-extremal case. So if this is the event horizon, so let me draw it as an outgoing null happy surface. Okay, and I consider sections, spherical sections of the event horizon. Then we can integrate over any such section the scalar field and the derivative of the scalar field. Y is a vector field, so it's a derivative. And this vector field is transversal to the event horizon. Not tangential, but transversal. It's an appropriate transversal derivative. So there is an expression that one can take of the scalar field and its first order transversal derivative, integrate it over any section, and get a charge, get an integral. Now, the fundamental property of the extremal case is that this charge is conserved. So in other words, it does not depend on which section you choose. If you consider the initial section and your initial data for the perturbation are such that on the initial section, this number here is 1, which is something very natural to do, then this number, this integral will be 1 for any section of the event horizon, even for the sections that live at very, very late times. So this is a conservation law on the event horizon, which again, it's a special property of the extremal case. And it's of course a consequence of the fact that the extremal case has 0 temperature or 0 surface gravity. Okay. So what do we get about this conserved charge? So, as I said, okay, we consider initial scalar perturbations which are initially localized to the event horizon, so we will consider that this conserved charge is non-zero for our case. And now let's study the dynamics. I don't know, the picture is very bad. Let's study the dynamics of such scalar perturbations. First of all, along the event horizon, in the extremal case, first order derivatives converge to that number, that conserved charge, which, as I said, generically is non-zero. So in the extremal case, first order derivatives generically do not decay because they converge to a number which is generically non-zero. And second order derivatives of the scalar field, in fact, grow linearly in time. This is along the event horizon. So along the event horizon, we have a horizon instability. We have expressions of the scalar perturbation which grow in time. Okay, the second one, this is growth. If you go away from the event horizon, sorry, this is not it should be an arrow. If you go away from the event horizon, all the expressions go to 0. So this instability, this growth, only happens on the event horizon. And this is the reason why we call this conserved charge as a horizon hair. It's horizon because it basically gives rise to horizon instability, horizon growth. And away from it, all the expressions go to 0. And it's a hair because of the same reason. It's on the horizon, it does not disappear in the evolution. It's conserved, so if it's initially 1, it will always be 1. Okay, so this is horizon stability for extreme black holes. That's what I did during my PhD. And since then, there have been many extensions of these works in other settings by various people. Okay. So I want to see if we can use this expression here, this conserved charge, this horizon charge or horizon here, to study the asymptotics of the scalar perturbation everywhere. Now, on the event horizon, at constant radius, hypersurfaces, and at null infinity. So first of all, if you are at the constant radius hypersurface, away from the event horizon, on an extremal rising ortho background, then you see that the limit of the scalar perturbation appropriately scaled in time is given by the conserved charge. So it's not now the weak field dynamics that give you the asymptotics of your scalar perturbation away from the black hole. It is the strong field dynamics. It's exactly the conserved quantity at the event horizon that gives you the asymptotics at constant radius hypersurfaces. And if you go at null infinity, and you try to find the asymptotics of the radiation field on null infinity, then you have here the top order term in the asymptotics. The decay rate is 2 again. And the coefficient is the conserved quantity h, which arises from the event horizon, and the expression I1 that we showed earlier. So I1, as we saw before, is given by the weak field dynamics, is the integral of the radiation field over all null infinity. H is the expression at the event horizon. So if we rearrange this dynamics, this equation, what we get is that H can be computed if you know I1, which is again the integral of the radiation field, and if you know the limit of the radiation field. This is radiation field, this is radiation field, that's H. So in other words, H can be given purely by information given at null infinity. Or and the left-hand side is precisely our signature. So our signature is the conserved quantity. So that signature that I told you that jumps discontinuously once you go from sub-extremal to the extremal case happens to have the physical meaning, which is the conserved charge at the event horizon. It's the exact expression that produces all this growth at the event horizon. And that expression, via this analysis here, can be measured purely by information at null infinity. So this is my last slide. This is the signature. This is the result we get in the extremal case. And let's try to see 3 conclusions. The first one is that the information seems to leak from the event horizon of the extremal case to null infinity. This is, again, information purely at the event horizon. This can be computed in null infinity. In an asymptotic sense, information goes from the event horizon, the strong field theory, to null infinity. And this is in sharp constant, as we saw before, with what happens in the sub-extremal case. The second conclusion is that extremal black holes do admit classical, externally measurable hair. This is the H. So this here is the H, and it's classical. Everything here is classical. And it's externally measurable in the sense that it can be computed by null infinity. And the third conclusion, that this horizon here could potentially serve as a true observational signature of extremal black holes. So since this is partly an astronomy conference, maybe I should show you a picture of my universe. Thank you.
So I have 2 questions related. The first is, I would think that the third law forbids the formation in finite time of extremal black holes. And the second is, you're looking at neutral fields, neutral scalar fields. I would expect them not to probe the charge, so they would be, in fact, analog of axisymmetric fluctuations around Kerr. So if I want to see the full, let's say, response of Kerr, I would expect it to be within charge fluctuations. Do you have any comments or thoughts on that?
So about the extremal case, so as I said, okay, one would be interested, let's say, near extremal black holes. So to do this mathematically, it's quite challenging because you have to have exact estimate for bounds of operators, which is very difficult to do. But numerically, Kana was able to show the following. So extremal black holes is a solution to the Einstein equation, so they are true solutions. And we have the right to study them, at least mathematically. Now, whether they form in nature or not, that's a different question. in view of all this work about highly spinning black holes, which are very close to extremality, one would like to understand the following. So this is time, this is the signature. And let's assume this is, sorry, let's take this back. So if a black hole is a sub-extremal, then this signature, in the sub-extremal case, will do something and then will go to 0. But in the extremal case. And this is a period where the quasi-normal modes work. Now, in the extremal case, the signature will do something here, but then it will not go to 0. Now, if you're near extremal, then the expectation is that, okay, you have the quasi-normal modes, and if it's near extremal, then the black hole will try to imitate the extremal behavior, but precisely because it's near extremal, then it will have to go back to 0. So there is this Trazen region after the period of quasi-normal modes that imitates extremality. Okay? So this signature is not completely irrelevant, even in the sub-extremal case, which is more physically relevant in that sense. So this is a transient signature. And this is part of the work, the numerical work of Kana. Now about the extremal care. Again, these perturbations that we study are axisymmetric scalar perturbations. Even in the case of real, neutral, scalar perturbations, the non-axisymmetric modes are extremely interesting. The behavior is even much worse there, and not everything has been understood mathematically. So, I mean, the answer to your question is that there is more work to be done in the charge and non-charge case, for sure. And the things that we don't know, even mathematically or numerically, are very interesting. Very interesting. And because the behavior is even worse than what I presented today. Yes? Sorry.
Yeah. How long, I guess the duration of that region you circled must go to infinity as you approach extremality. How does that behave?
Yeah,
if we take how does it depend on the deviation from extremality?
Perfect. So I remember that in order to start seeing such a region, you need to be at least something like that, which is quite close to extremality, in order to even see such a region.
But can you say whether it's a power or a log or an exponential in the?
You mean the length?
Yeah, how does it behave with the deviation from extremality?
That I don't remember. I mean, I haven't seen the full work of theirs. Just communication by email, so I don't.
Yeah.
Yeah. Sorry.
Okay. Thanks, Stefanos. So our speaker before lunch will be Michael Poole, and he will tell us about binary black holes merger observed by LIGO Virgo during the first and second observing round.
Sure. I'll try. Sorry? You show me 5 minutes before or something. 20 minutes. Okay, yeah. So thank you very much for inviting me here to talk about binary black hole observations from LIGO and Virgo during the first and second observing runs. So here in the title slide, I want to point to the two papers that I will talk about. First one is the catalog paper. The second one talks about the population of binary black holes. And you're also very welcome to look at the link that I posted here to look at the actual data products. So you're probably familiar with the detector network. So we have the two LIGO detectors, Livingston and Hanford, and the Virgo detector. And let me say a bit about detecting gravitational waves from compact binaries with LIGO and Virgo. So assuming that we have a signal from a compact binary coalescence in the detector data, there's basically two options of how we can learn about that signal is either a cross-correlation or matched filter search, or we look for coincident excess power. So the first one assumes that you know what the waveforms are that are in the signal. So you have solved the two-body problem in GR, and you've gotten your waveform templates for binary black holes. And then you make a bank of templates out of those, and you filter the data with that. And we have two searches that use that method. And the method B, looking for coincident excess power, doesn't use a waveform itself. It just looks for this excess power, and it can also assume that the signals are chirping so that the frequency is increasing with time. Okay, so we have these two searches. Now, what we actually want is we want triggers that are coincident in each of the detectors, at least more than one detector. So for method A, we identify single detector triggers. We use a tailored statistic to do that depends on the signal-to-noise ratio. And then we look for temporal coincidence between the events in different detectors. And for method B, we look for events that are coherent in multiple detectors. And there have been some improvements over the O1 analysis based on what I'm showing here. So in case you are not familiar with matched filtering, the basic idea is that you have some detector data, some time series, it's noisy, and there's some signal in there. Then you have a template computed from solving the two-body problem. And you also need to know the power spectral density of your detectors, shown here, and then putting all of these elements together, you can compute an inner product between two waveforms that tells you about how similar or dissimilar waveforms are. And so that's the basic method used in matched filtering for extracting extracting signals from noisy data. Now, before I go to the detailed properties of the systems we've observed, we need to talk about which are the significant detections and how do we qualify that. So we define a ranking statistic for the matched filter searches. What we do is we calculate a likelihood ratio of obtaining the trigger's measured parameters in the presence of a gravitational wave signal versus in the presence of noise. And for the burst search, there's a coherent network signal-to-noise ratio that's computed. To talk about significance, we need to know about the background distribution. So how do we learn about that? What we do is we time shift triggers from one detector with respect to the other detectors by an amount that's bigger than the light travel time between the detectors. So it's an unphysical time shift. And the resulting coincident triggers that we pick up are samples of the background distribution. With that in hand, we can define the false alarm rate, or FAR. So that's for each foreground trigger, that's the number of background triggers with equal or larger ranking statistic than the foreground trigger, dividing that by the duration of the data searched. Okay, so what are the actual selection criteria that we use to include events in the catalog? So we wanted two things. We wanted first to include, of course, the signals that are confidently astrophysical in origin, and we also wanted to include a set of marginal triggers where there may be some true signals in that data set, but there's certainly also noise triggers in there. And to do that, we decided to define two thresholds. So threshold 1 is a false alarm rate threshold smaller than 1 per 30 days. And threshold 2 is also a threshold on the probability of astrophysical origin being greater than 50%. I'm not going to say how this is calculated because it's a bit complicated. But if an event satisfies the two thresholds together, then we give it the GW designation. So these are our gold-plated detections. If a trigger satisfies only threshold 1 but doesn't satisfy threshold 2, then we designate it marginal. And these thresholds are to be satisfied in at least one of the two matched filter searches. And you can ask, why did we pick this particular false alarm rate threshold? And so the motivation is that for O1 and O2, any sample of events all of whose measured false alarm rates are greater than 1 per 30 days, is expected to consist of at least 50% noise triggers. That's sort of the contamination of noise events in the total number of triggers. Okay. Now let's go to the properties of the confident detections of gravitational waves. Let me just list them briefly. So in this analysis, we found 4 new binary black hole mergers that were first announced in December. And so these are these events listed here in red. And in addition, in this reanalysis, we also found that one of the events in 01 that was not as secure before is now also a GW event. So the significance has increased because the searches has improved. Okay, and just flashing this table here to show that, so in the paper, in the catalog paper, you can look up the detailed properties of all of these events, when they happened, what the false alarm rate was in from different searches, and what the network signal to noise ratio was. So now let's take a little detour before we learn more about the properties of these events. One important ingredient is how well do we know the waveform for these events, and what's the state of the art there, and what do we need. So we want to have a complete description of a binary black hole signal in this case. So here's a sketch of different stages in the coalescence of two black holes. So there's the in-spiral stage where you can use post-Newtonian techniques. Then there is the highly nonlinear numerical relativity for the merger stage, and then you can use perturbation methods for the ring down. So that's sort of the information that we need, basic information, producing single waveforms. But what we actually need in practice is we need parameterized models of the waveform. And these models need to be accurate, so we can extract maximum physics, and they also need to be fast, so we can actually do the analysis in a reasonable amount of time. And in the study, we used these particular binary black hole waveform models, so from 2 different families, as effective one-body models, phonological models. And these models have been tuned to numerical relativity for aligned spins. Some of these models support precession, either effectively or fully, but they haven't been tuned in that precession sector. Okay, so what about the different parameters that the gravitational wave signal depends on? Well, it's useful today to consider 2 different classes. So there's intrinsic parameters that describe the system itself. So we have a sketch of 2 black holes here in spiraling. There's the orbital angular momentum vector L, and you see the spin vectors of each black hole, and they can a priori point in any direction. Then there's extrinsic parameters that give you the relation of the source system with the detector network. So where and on the sky did the event happen? When did it happen? How far away was it? And what was its orientation? To learn more about these binary black hole coalescences, we perform parameter estimation, and it's done as follows. So if you suppose we have a stretch of data D, and we have a parameterized waveform model, H, depending on parameters lambda. And in the data, we have noise plus a true signal. Now, if you compute D minus H of lambda, and H of lambda is a good waveform model that can accurately describe this true signal, and you choose the right lambda, then you will essentially get just a noise. And so that motivates the definition of a likelihood function, where you compute the inner product, the noise-weighted inner product between D minus H and itself. And then using this likelihood function and using Bayes' theorem, we just write down the posterior probability distribution for the parameters lambda. Given the data and given models. And so, yeah, the models include the signal model that I've talked about. Also, we need noise models, so we need to know what the PSD is for each detector. And we need to specify the prior distribution for the parameters. And then we numerically sample the posterior distribution. And the overall result is given here. So again, is the table in the catalog paper, which I just wanted to point you to without going into details. What this table shows you is for each of the confidently detected GW events, it shows you medians and 90% credible intervals for selected source parameters. The numbers come actually from combining posterior samples from two precessing waveform models to average out the errors in particular models a little bit. And the new events are highlighted in red. And this is also consistent with the results that we had in prior publication for the events that had already been detected. Now let's look at a few plots. So here is the component mass distributions for the set of GW events. So you can see that there's quite a range in terms of masses. Here's the binary neutron star, and then there's all of the binary black hole detections. And so the lower mass systems, they have this funny banana shape, whereas the higher mass systems are just blobs. So the degeneracy that you see here for lower mass is just an expression that there is a better measured parameter than the component masses, namely the chirp mass. And this is important for long in spirals, so lower mass systems. Now, spins are an interesting observable. What can we say about the spins? Unfortunately, at the moment, it's very hard to measure the spins well, and there's 6 spin degrees of freedom. So what we prefer to do is we like to form combinations of spins that sort of effective spin parameters that give us sort of the most information that we can hope to get at the moment. And it's done as follows. So for aligned spins, well, you have again your sketch of a binary black hole system. You just project the spin vectors onto the orbital angular momentum, and then you take a mass-weighted combination of these two projections. That gives you this chi-effective parameter. And for precession, there's a more complicated definition here. That's basically an averaged spin in the orbital plane. And how well can we measure these? Well, let's look at the plots from the catalog paper. If we look at the top right plot first, so this is for this effective aligned spin, chi-effective, for all of the GW events. You can see that this is actually not so badly measured. And what you also see is that all of these posteriors include 0. There's 2 of them, though, where 0 is outside of the 90% credible region. So these 2 probably very likely have a positive aligned spin. And that means that at least one of these spin vectors of a black hole is positive. Now turning to precession, the story is at the moment we can't really tell whether any systems are precessing. So this plot will show, so for each event is the split violin where the left half of the violin is the posterior distribution, the right half is the prior distribution. Now, since they are almost the same, it's telling us that we haven't really learned anything given the data. So we have to stay tuned, and hopefully we'll be able to measure that in the future when detectors are more sensitive. Turning to extrinsic parameters, the distance and inclination are, of course, very interesting astrophysically. So this plot shows you 2-dimensional posteriors, 90% credible regions between distance and inclination angle. And you can see that there's usually 2 modes in the inclination. And for some of them, well, for some of them is 1 mode, but overall it's this 2-mode behavior, and there is if you have inclination 0 or pi, then so it's face on or face off, then the signal is strongest. If you're in the middle here, then you're looking at the binary system edge on, where the signal is the weakest. Looking at the plot on the right, what's plotted here is luminosity distance, or redshift, against the chirp mass. And what we can see is that there is a positive correlation overall. And that's telling us that these gravitational wave signals are not affected by lensing, because if you go to higher chirp mass, the gravitational wave signal gets stronger. And so that's exactly what we expect. So this is another depiction of what we know about black holes. And so we have the LIGO Virgo black holes here towards the top. So on the y-axis, we have the masses of these black holes in solar masses. And we also have the electromagnetic observations from X-ray binaries here. And so this is a curious thing that the LIGO Virgo black holes are heavier than the electromagnetic black holes. So that segues into my last few slides, where I want to say a bit about the population of binary black holes, in particular the mass distribution. So far we've seen 10 binary black holes in O1 and O2. And these, as I've just said, these binary black holes from gravitational waves are heavier than expected from X-ray binary observations. And they're also heavier than were previously predicted by astrophysicists. But we can form them if you have the right environment, if you have low metallicity and particular stellar winds, then you can get them. What I've already mentioned is also there's the selection effect that more massive binary black hole mergers emit louder gravitational wave signals. And so that means we can detect them at higher distances. And that may partly explain why we see a preponderance of events that are, let's say, 30 to 40 times the mass of the sun, as opposed to those that are lighter, with 10 to 15 solar masses. Then there's also regions in mass space, so-called mass gaps, where it's suspected that there may not be any black holes. And so it's interesting to see where our observations lie in comparison with these. So first, what does the mass distribution look like? So the ansatz we made in the past, and the simplest ansatz that you can make probably is to say that you want to fit a power law distribution. So you have P of m is m to the minus alpha, and what's the index alpha that fits best here? We have a very simple model with fixed bounds for the low and high mass, then you get this exponent 2.3. You can consider more complicated models. So you can allow the minimum and maximum mass to be free parameters. You can add also information about the mass ratio distribution and fit that at the same time. And you can add an additional thing for one of the mass gaps. So there's a prediction by supernova modeling that there will be a gap in the black hole mass spectrum around 50 to 130 solar masses, and a buildup of black holes around 40 stellar masses. And so that comes from the so-called pulsational pair instability supernovae. And so we can add like a Gaussian component at high mass to put that into the model and see how that performs. And if you do all of that, you get a number for the power law for the power index of 0.4 with these error bars. So at the moment, we're not able to really constrain that very well. But this will improve as we detect more and more of these coalescences. So for the population paper, let me say that this is really a very quick look at some of the results, and there's a lot more in that paper if you haven't checked it out yet. So the one thing I do want to show is the mass-dependent binary black hole event rate distribution. So what's shown in this plot is the derivative of the rate with respect to the mass of the primary component. And as a function of the primary mass, so the bigger black hole, the dashed lines show you the posterior population distribution. That is the best prediction for what mass a typical population member might have. Then there is 90% bands around those, and you see the three different models that are being plotted. it's a little bit messy, and the complexity increases from Model A to Model C. So Model A is just the power law model. Model B also includes the mass ratio distribution. Model C includes this Gaussian component at high mass to capture this supernova mechanism and this buildup of black holes there. And what you can see from all of these together is that if you look here, there's almost no black holes being predicted at masses of 45 solar masses or higher. And so that agrees with the predictions from supernova modeling that we currently have. And then you can also compute the estimated binary black hole merger rate, of course, here under the assumption that the distribution is uniform in co-moving volume. But at the moment that's a good assumption. And that gives you a number that's between about 10 and 100 per gigaparsec cubed per year. And then finally, to conclude, so we found in 01 and 02, we have made confident detections of gravitational waves from 10 binary black holes. That includes 4 new detections. And so that was approximately 1 gravitational wave detection per 15 days of data searched. Determined this binary black hole merger rate that I've just quoted. We haven't found any evidence that there are binary black holes in either of the putative mass gaps at the moment. So the other mass gap that I haven't described yet is the one between the heaviest neutron stars and, I guess, the lightest black holes that were found from X-ray binaries. So that would be between 2.5 and 5 solar masses. Okay, then to conclude the third observing run now of Advanced LIGO and Virgo, 03 has started on April 1st. So we have been taking data and new things have been coming in. So you may be interested in what have we found, but of course there are public alerts, so you can look up some of the parameters yourself. And the general expectation is that there will be many tens of observations in the coming years. Based on the 01 and 02 event rates and the analysis, the number that was given, I think, at the Amsterdam town hall meeting is 35 plus 78 minus 26 binary black hole events during 03. If you translate that, that would be about 3 per month. And that's roughly consistent with what we're seeing now. So in April, we got exactly 3. Now we seem to be getting a bit more. So things are looking up, and many interesting things are going to come our way. Thank you for your attention.
So, Michael, you had a plot where, actually a table where you could have an estimation of the spins. And before you explained the chirp, there it seems that there's an average, like a golden ratio of a spin of 0.7 on average in all the observations for A. Is that? Maybe it's, if you go back, there's a table with the chirp masses before this one. Yeah, so the AF is the estimation of the spin parameter.
This is the final spin. So this is the spin of the final remnant Kerr black hole.
Right, but so if you look at the average, there's a golden ratio there. There's a 0.7 that all the gravitational waves. Is there an explanation that has to do with perhaps using semi-spherical orbits, or is it related to, I mean, do you have an explanation for that?
Well, yeah, I mean, this is understood mostly numerically, and it, also the fact how is this number actually computed? You can ask that. Because there's some mapping between the component spins and component masses of your binary system to the final state. And so the way we can most accurately determine that is by performing numerical relativity simulations and then interpolating the data that comes from that. And so that's done. And if you have, now to your actual question, if you have non-spinning black hole binary, you will get a final spin of approximately 0.7, so a little bit below that. And that explains, so if you also look at the, remember this plot here of the distribution of the effective spin, this is around 0. Now if you have this distribution, you expect to have a final spin distribution that's around 0.7.
Thank you.
I have two questions. One is, you basically skipped discussion of the criteria for determining whether an event is astrophysical or not. I wanted to give us, I wanted you to give us some more details, especially considering the recent black hole neutron star alert, and explain what's going on to determine whether an event is astrophysical or not. And also I would like you to comment on, well, the alerts are public, so there's about 11 as far as I know right now. Are the rates still consistent with the estimate that you gave in one of the last slides, or can you comment at all on that?
Yeah, let me take the second question first. So out of these 11, I believe, so let's concentrate on the binary black holes. So let's eliminate anything that's not a binary black hole. And I think doing the math, subtracting these, and also there were 2 retractions. I think the current number is about 8 at the moment, 8 binary black holes in O3. Now, these are just based on the false alarm rate criterion, the 1 per 30 days. So these may or may not be all GWs. So some of them may not be. Now, with the public alerts, there is some computation of the probability of it falling into a particular binary category and also being of astrophysical origin. That is not the full calculation that we did for the catalog, which is much more involved. So how exactly these numbers would change, I cannot say at the moment. So with this number 8 binaries, that is now in the month of May, you could say we've gotten a bit more than we expected. We'll see how it develops further. There's different things that come into play there, different assumptions that you make for this prediction that I showed. And it could just be that the duty cycle of the detectors is higher than we expected, that they're on almost all the time, and so they're finding more things. There's many factors that go into that. Regarding the computation of the probability for different criteria and being of astrophysical origin, what's being done is there is a Poisson there is a Poisson process for each category that's being modeled with a mean count, and so it's a mixture distribution that's being looked at. I'm not really involved in that particular part, so I'm not the full expert on how this is done, and it's sufficiently complex. I think we can discuss it offline probably.
At the beginning you said that maybe the detection of massive, that they were heavy, could be a selection effect, but then you talked about the distribution that you would expect, and presumably you know how many of those you should see. So has there been any quantitative analysis on whether or not you are seeing the rate per mass that would be consistent with what you're claiming should be there?
That is a good question, and I must admit I don't know the real answer to that question. I mean, we certainly see detections over a range of distances that's quite wide, and yes, the events that we see that are most far away tend to be very heavy systems, which is exactly as expected, because if there were lighter systems, we wouldn't be able to see them. The SNR would be too weak. But a detailed analysis along the lines that you point out, I'm not currently aware of.
I mean, it might make sense once you have the 30 extra events, but it would be interesting to know that.
I agree with that, definitely, yeah.
Well, we're always interested in distances, and you gave a table of distances and redshifts
but it must depend on calibrating the absolute strain of the detectors, because that's the thing that you measure that depends on the distance. So can you say a little bit about how the strain is calibrated and how accurate you think it is?
That is again a good question. So I cannot describe the full calibration model because it is sufficiently complex. I can say one thing. In the detailed analysis of the properties of the black hole binaries, we take into account this uncertainty in the calibration. So the people, the experts on the calibration of the detectors, they put together a model of what this should look like, basically telling us how uncertain it is. And we fold that into the parameter estimation by applying that uncertainty on the waveform template. And then we have these additional parameters that describe the uncertainty, and then we marginalize over these parameters at the end.
But at the beginning, how do you tickle an interferometer by a known amount to measure how much strain produces how much signal?
That is a good question. This is, I'm sure for an instrumentalist, it's easy to answer that. Do you know it, Max? Yeah.
Have to push the mirror.
Yeah. Yeah. Yeah.
Radiation pressure on the mirror. Yes, that's one of the main ways. There are 3 lines of each interferometer.
Carl?
So the uncertainty scale that Michael mentioned is measured to this extra laser system is a little over 3%, so maybe 3%. The uncertainty caused on the distance caused by the uncertainty from the calibration is much smaller than the uncertainty on the distance itself. And at the moment, it's not expected to be.
That's right, yeah. I mean, the statistical error in the distance is much bigger. If you look at the posteriors, they're pretty wide usually.
I was curious, as someone from the outside, seeing some of the data becoming public and then a group at Princeton claiming that they detected additional events. Did you see these events to start with and just concluded that you're not confident enough to make them public? Because that affects the calibration of the rate, of course, if you have extra events that you missed or other people made.
Yeah, that's a good question. So we did not see them in our analysis, otherwise we would have included them. So they're not of GW type. I think some of these triggers that they published, though, we do see in our searches. And our searches are different from their searches. So there's some technicalities that I don't want to go into and also not an expert on. So we do see them as marginal triggers. So I think in the list of marginal triggers that we have in the catalog, I don't think these are included though. So there must be some other reason that I would need to look up where exactly they are. But I think it's great that the group at Princeton is doing this analysis, and they're inventing new techniques, and it's great that they're doing this independently, and it may help us like both find out how to do things better, how to improve the methods, and perhaps also at the end of the day, find out why there are these technical differences, and finding this event and in this particular search, but not in this particular search because of the different binning in the mass space or other things. Maybe they used a different template in the analysis, and that causes a difference. I think it's worthy of further discussion about that, and it's a great thing to have.
Yeah, in your mass distribution, you're having a hard cutoff at 5 solar masses. Why? I mean, you have a new way of looking at the universe. Why cut it using some bias that comes from other type of observations?
So I think there's different models that are being used, as I mentioned, and some of them have this. So the simplest model, that I showed here, just the power law in mass, indeed has this hard cutoff at M1 of 5 solar masses. But the more complex models, they allow these bounds to be free. So these are parameters you fit for. And so I think this is not imposed.
Okay, let's thank Michael.
Thank you.
As a lunch will be served outside, so I'll see you at 2.